So as you know, this session is going to be recorded. So Josep Luis, thank you very much for accepting the invitation to do this lecture today at the ACM Summer School, right? So thank you very much. Josep Luis Berral is leading one of the groups at BSc. Josep Luis, I don't remember now. Yeah, here. Thank you. You have it written here. The data-centric computing group, where I mean he's working on his main topic that he already started in the PhD and before, about how to manage data centers using AI. So how to use AI in the different forms to manage different aspects of data centers. In fact, this summer school is a clear example of the genealogy of researchers. So Josep Luis Berral was a student of Jordi Torres, Professor Torres, that we had this morning the lecture, right? Jordi Torres was my student, so we have here 3 levels. Yesterday you had the lecture of Professor Jesus Labarta. He was my advisor, so 4 levels. And finally, tomorrow you will have Mateo Valero in the afternoon. I think it's going to be the last session tomorrow in the afternoon. So Mateo was the advisor of Jesus Labarta, right? You see here 5 generations. This summer school seems to be a family managed affair, you see. And in fact, Rosa Maria Badia, that was lecturing yesterday afternoon about PyComs and workflows, was a student of Jesus Labarta too. Marc Casas was a student of Rosa Badia and Jesus Labarta. So you see, I mean, it's a family-run business. Okay, but so joke part of that. So thank you again, Josep Luis. And again, we will have today a very practical session, right, Josep Luis?
Right.
So you will be switching between slides and practical contents that we will enjoy also very much as we enjoyed this morning with Professor Torres. So again, thank you, and you can start whenever you are ready. Thanks.
Okay, thank you, Eduard. Okay, so everyone's here, I guess. So we will start now. This session, it's distributed data analytics in supercomputing systems. What we will see here is about distributing analytics or analytics platforms that distribute in large-scale systems, or that can be distributed in large-scale systems, among them supercomputers. And during this session, what we will do is kind of a hands-on, where I will be doing stuff while you can do it at home. And remember that we shared with you the manual to set up the environment. That I will explain it again. Do not worry. And at the end of the session, we also will try things in Mare Nostrum. So we will try to do things first in a small machine, in our machines at home, etc. And then we will see how to port to Mare Nostrum or a big supercomputing machine. All of this, having in mind that the kind of workloads and executions that we want to do, the kind of operations that we want to do, will be related to data analytics. And for that, we will use Spark. That's what I'm going to introduce you now. Let's see if I can change. Okay. So what's this all about? So we have big data analytics. Big data analytics is a scenario where we want to do analytics on data, but the data is so large, it's so huge, or it comes so quick to our systems that the classical methods do not work. That we cannot just store some data in our machine to analyze, or we cannot run some classic script over data because it would take too long, or it would use all the memory to read a single entry or a bunch of entries on this data. So that's more or less what we call as big data here. That is, what if we have enough data that we usually wouldn't be able to do with our classical software? And for that, we use distributed systems. That distributed systems is basically if we don't have enough with one machine, or that we can leverage parallelism. So let's parallelize it. Let's try to see how we distribute this data or these operations over data in order to not to take so long, or to be able to analyze this data in more depth, or just to run more experiments or run more analysis over data. So this is the environment here. I guess that you can see my pointer moving because I'm sharing the screen. You should be able to see this hand here. What I don't see is the chat.
We do.
No. You do. Okay. Also, I think I can enable here the chat in case that anyone has a question. Okay. Now, perfect. Thank you. So there are many applications and many frameworks to run big data. Basically, the past years have been this boom of big data analytics, because we suddenly found that everything, every data, every piece of data that comes to our systems can be analyzed, for better or worse. And a lot of people got involved in creating data analytics platforms. The one that we will focus today is in Apache Hadoop and Spark. Specifically Spark. I will introduce you Hadoop a little bit just to have the main idea, but we will focus on Spark as an example of different platforms to run analytics. Also, Spark is one of the most known or most extended in the industry and also academia. So if we have to choose among several, maybe this will be more interesting. But one important thing is that even if I explain here about distributed systems for data analytics, etc., with Spark, the same concepts, the same ideas of how to split data, how to process data in different things, it will be the same in Apache Spark or in other platforms available, even TensorFlow or even the same Hadoop by itself, etc. So the important thing is that you get the idea, and just we use Spark for playing a little bit with it and seeing what happens. Then we will have one of the things that has Spark is that has some specialized libraries. Spark exists because, informally speaking, because some people from Hadoop, that was a distributed processing framework, so that it was being too much generalist and then inefficient, because not inefficient by itself, but that some things could be done better with specialized libraries. And they started to think about implementing these libraries inside Spark. Spark has many qualities, but one of them is that we have a library like Spark ML, previously known as MLlib. If someone is familiar with Spark, they try to change the name at every version, but people still think about MLlib, but let's call it here Spark ML. And also another library, Spark Stream, that we will see of how processing data in streams, meaning that we don't get a batch of data and just process it, but we set up our environment as a pipeline of data that comes, is processed during this pipeline, and then we got the output somewhere else where it is needed. And what about the environment? We will see here things like containerization and automatization for HPC. There are several platforms for containerization. I will explain you containers in case that somebody is not familiar. The containers like Docker, Kubernetes, that's a manager of containers, and also Singularity, that's a container environment prepared for high security systems or highly secured managed systems like would be the Mare Nostrum, in order to run things in an isolated way and portable way, that you don't have to install or configure lots of things, that you have everything prepared in an image, and then you just deploy it when you need it, where you need it, and then get rid of it when you don't need it anymore. So let's move on. Okay, this will be in three parts, this session. First, I will explain a little bit of how things work with distributed systems, file systems, also containerization and environment. Then I will go to the details of Spark here. I will show you some examples that you will be able to run at home. And finally, we will go with hands-on in the supercomputer. For this session, we have 4 hours. Originally, it was expected, or they gave me a slot of 3 hours, but as I crafted this session from a bigger one, just selecting the important topics for now. I considered that maybe 3 hours was, we were short, and I asked for an extra hour. So this will be between 3 and 4. And I hope that I didn't compress it too much, and we have less hours. So I guess that I hope that we will be able to see everything with its correct piece, time and time. So let's begin. We're setting up the environment, or seeing which environment we have. So we have Apache Spark. I told you, oh, Apache Spark, what is this? This is a platform for processing data, and what it has of interest is the kind of scheduling in distributed systems. So with Spark, it's not like other languages that you directly tell the system what you want to do and then just run it one by one, but it's more like you have some data, you want to apply some functions, some transformations, some ETL process of extracting, transforming, and loading data over your data. And then Spark sees this data, if it fits in the different working machines, and how to split it and how to run these functions in an efficient way. So when you tell Spark or a platform like Spark, please get this data, apply this set of functions, and then store here, what Spark does is, okay, you're telling me to get this data, let's internally optimize how I can split this data. You told me to run these functions. Let's see how to optimally run these functions given the data split, or even modifying the data split in order to be efficient when running the functions. And when storing this data, see how to efficiently collect all the results and store them. So one of the important things of this kind of platforms is an optimizer, that you as a user or a scientist running the analytics, you don't you can focus on optimizing your functions, but when optimizing the way you split the data and apply these functions over this data, you let it Spark to optimize it for you. You can do it manually, but the usual thing is you let Spark, and then you optimize by your size if your function can be more or less efficient. But about where to place the data and process it, you leave it to Spark. That's one of the advantages of these kind of platforms. So what Spark does is orchestration, meaning that you tell Spark what to play, which data to be processed, and then Spark tries to see where this piece of data will be in each machine and which functions will be done and in which order, in order to have them as fast as possible, as efficient as possible to run. And also the libraries here, libraries for distributed ML and streams, that when I explain you about the ML and streams function, I will explain you a little bit how these algorithms, the algorithms for distributed machine, for machine learning or streams, are prepared to be run in parallel. Because one of the important things is that the different functions, different aggregation functions, transformation functions, etc., that the libraries have must be prepared in order to be run in parallel. Here, the idea at the end is that everything must be prepared to run in parallel in the system, and the thing to optimize is how we distribute it properly in order to be efficient. So how we deploy this, how this actually works? Well, we imagine that we have a cluster. We have a cluster, a supercomputer, set of machines on the cloud, and you have to prepare something to run these things. Then in Spark and other kind of platforms like Spark, what we have is masters and workers. The masters are the ones that receive the applications and must be responsible. This is the part of Spark that's responsible of reading what you're submitting seeing how to split it, and see how many workers you have available. So basically, you submit, a user sends a Spark application. This would be a script done and prepared for Spark in any language that Spark admits. You will see now. It submits to the master, and the master says, okay, which workers are available, and also for the file system, means where is the data and how it is distributed. And then the master optimizes this execution plan, the script you submitted, and then orchestrate the workers to see which ones are available at each time, to which workers send this data, and to which workers send to execute some function. So we will see that we have this architecture, this structure of pipelining for our data to go up and down and be processed. Then we have the distributed file systems. This is I will explain you now, but we will not use it at this time. I just want you to know that this exists and that this will be interesting if you deploy some kind of architectures like this. The thing is that we don't have enough time to do all the practical part of this, but I want you to know it and see that this exists. So everything started with Hadoop. Spark also started with Hadoop at some point. And basically, Hadoop, what did is a distributed computing engine. This means, again, you give some data, some functions to execute, and Hadoop was in charge of splitting data, executing functions, and collecting the results and putting them together. But Hadoop, one of the things that remain, and that's interesting, is the file system. Meaning that Hadoop, aside of an engine to run things, it had also an engine to store things. And this is the HDFS, the Hadoop file system. And what does the Hadoop file system do? Well, it's an architecture like this, meaning that we have a client machine. That's the one that's trying to run things over data, that the one that's trying to acquire some data in order to execute whichever function needs to be executed over data. And then we have a set of data nodes. That these data nodes are nodes with some storage, and that they store the remote files. So the idea is that at the end, the set of files stored in across these data nodes are seen as a file system, a set of files, a set of directories with files that can be retrieved, that can be pushed inside, that you can move, rename, and ask for them. For these data nodes, so the function of these data nodes is to store this data, but also to keep this data safe, meaning that if you're familiar with the concept of RAID storage, I don't know if you're familiar with RAID storage, when you have a RAID system of disks. I'm checking the chat just in case that somebody says, hey, I don't know about this. Well, when you have a RAID system, you know that you can put everything distributed across disks, or you can put replicas, meaning that if you have files 1 or A, B, and C, you can put file A in machine A1, file B in machine 2, and file C in machine 3. But what happens if one machine fails? That you lost part of the data. So one of the things that you can do is setting replicas, meaning, well, file A, imagine that this is file A, this, no, oh, wait, no, I cannot click, I just can hover over the slides. If you have file A, you can say, okay, I put A here and the replica of A here. Then here I can put file B and here a replica of B. And then I can put here C and here a replica of C. So in case one of the data nodes fail, you still have other data nodes with these files available. And also, not just for replication, but for efficiency, what if we, instead of one client machine, we have several client machines accessing to different files? Imagine that we have file A and one client machine is accessing. And the client machine, what does is, okay, name node, tell me where is file A. The name node tells, look, it's in data node 1. The client machine goes to data node 1 and asks for file A. But imagine that we have 1,000 clients accessing to data node 1 for file A. If we have replication, the name nodes can do a round robin, meaning that for each client, it says, okay, file A, this is the machine 1. And the next one that comes says, oh, file A, it's a machine 2. And the next, oh, A is in machine 3. And then back for the next to machine 1, 2, 3. So we can parallelize the access to files in case that either our application of data analytics or different users or clients running things into this platform to have more available these files instead of having just one bottleneck of a single machine holding this single file. Here people ask, how many name nodes are usually needed? Well, it also is interesting, this question. At least one, obviously, because you need to know where the files are, this is the directory. You can set different name nodes. You can replicate name nodes in case that you have thousands or millions of client machines or client applications asking for names. So you have to scale these. You can set one as minimum, but at the moment that you start to have load, you need to start replicating this. There's not a magic number, meaning that relative number, it's difficult to say 3. No, because if you have a very large system, it depends on the load that you have. Usually, it is done a little bit by trial and error. There's no magical formula. You usually provision some machines to do as name nodes, but if you see that they are some of them they are empty, you can reduce the number, or if you see that they are overloaded, you add more machines. So you have to resize it. It always depends on your environment, because no environment is the same like than others. So actually, sizing the name nodes, sizing the data nodes, sizing the replication, and sizing the workers is one of the main jobs of people working in clouds and in this kind of platforms, or people trying to develop algorithms that automatically open and close these machines. So sizing this kind of system is something that is mostly automated at this time. A few years ago, we had a person that went to see the machines and started it or shut it down. Now, usually we have some schedulers and we have some managers that I will show you a little bit, or I will give you the idea when we see containers, that in case that we detect that our name node is totally overwhelmed, then we start a new name node and we send half of our clients to the other name node. When we see that the name nodes are underused, we start shutting them down. Also with data nodes, we can do the same. It's more tricky because we have to share data. When we start a new data node, we have to replicate some of its data. That if we replicate it in parallel, that's not much of a problem, but it also takes time and effort. And also, if we remove a data node, we must be sure that we are not leaving any file unattended, meaning that we are shutting a machine with a very low number of replicas of that file. So this is a little bit the current state of the art of autonomic computing, self-management, and machine learning for managing data centers is basically on how to decide when we put more machines like this, and see the costs of it, and see the opportunities also to add or subtract more machines. So it's a very important question, actually. So also it depends on data, also volume of data, volume of requests, of applications, of people putting load into your system. So we have this distributed system, and although we will not be able to experiment much or to experiment with it at this time because of time, just for you to know that this exists. And the reason of having it alongside data analytics platforms is because first, we have the data distributed, meaning that if our data analytics platform can leverage the fact that the data is already partitioned, that it's not in a single place and it has to split it in parts to send to the workers, but it is already split and each worker can access to a data node and get a piece of data without saturating any storage server or without saturating the master node splitting data. So the usual thing is to have these kind of file systems next to the working node. So we have data nodes and workers from Spark, TensorFlow, or other platforms all together. And when we create these applications, we try to split things in a way that's even for processing and storing. So that's a way of combining storage plus the processing. Okay, let's continue a little bit. Then we have the containers. This is I explained the technology of Hadoop. I explained it, and I'm explaining now containers. So, what are containers? In case that you are not familiar, this is what we're going to use. In the previous sessions or previous versions of this course, I used virtual machines, but now we have containers. That's a step forward in some kind of aspects of encapsulation. So imagine that you have an application and you want to set it up in a way that you want to be, first of all, portable, meaning that you don't need to go to every machine and configure it with a software, install a software, check that everything works, do some tests. What happens if the machine goes down? You have to reinstall it again. Maybe you have to reconfigure again. You have to check every peculiarity of every machine. That's a kind of a hell of management. With containers and previously virtual machines, the idea is that if we have an environment, for example, like Spark or an environment you want to run, what you do is to prepare an image. That's the image. That's basically the encapsulation of the environment. This means that you define an environment with a software installed, with a configuration prepared, and you know that when you run this image, it always will be the same. And if you configure it right, it will always work. So it doesn't matter if you're running things in machine 1, machine 2, machine 3, etc., that you will have the same environment and it will be a clone of each other. So basically, this is it's in an in-between as just installing things as is and a full system virtualization. I guess that you are used to virtual machines. You know the concept of a virtual machine, right? Yes, if somebody doesn't know, just tell it. So with a virtual machine, the thing is that you have an application running in your system that implements a hardware layer of a virtual machine, a virtual computer. Then you have installed the operating system, the frameworks, and finally your application that you run. And you can shut down the virtual machine, create a copy, bring to other machines, start them again, etc. With containers, we remove the hardware virtualization and also part of the operating system virtualization. What we have is an environment that will take the most that it can. Imagine that this is the container, the layer of container execution. You have a hypervisor that allows you to run things as containers, and you have the operating system down and the real hardware. This layer here will pin what it can from the operating system, will access that, will access through the operating system to the hardware. So it will be lighter than a virtual machine. A virtual machine, you have to boot up. It has to start the operating system. It has to start the daemons and the applications. With the container, just start the application, and you keep with the container the few libraries that you need to run this environment. So the thing is that imagine that you have a repository of images. This means that you have this environment. For each environment, you have an image. You have a repository of this image. And when you need to run something, you grab this image, create a copy of this image, and put it to run in your system. That's an instance. That's what we will call an instance. It's a deployment of an image, and you can deploy as many instances as you want, in case that you want to run this environment several times, and for each environment, give the data you want or the functions or executions you want to run in this environment. The things of containers is that unlike virtual machines, they are thought to be volatile. This means that a virtual machine, you start it, and if you want to stop it, you can stop it or freeze and keep the things inside, meaning that you can restart the virtual machine later with the same status as it was. You have some persistence. The containers are created with the idea, they can also be persistent, but they are created with the idea of being use and drop, meaning that you create an instance, you execute whatever you want in the instance, and you destroy the instance. So if you have some results, you keep in the system, because you don't virtualize in a container all the full stack. You only virtualize kind of the application layer with a little bit of libraries and operating systems. So in a container instance, all the persistence will be stored in your same machine or in a distributed file system, meaning that the storage will be away from where the container is executed. So it's basically, I want to run application A, or environment plus application labeled A. I just run. When it's finished, I drop it, and that's it. And what we will be using this for? Because, for example, I have prepared for you a container with Spark prepared. So you will only need to create an instance of Spark in order to run things there without installing anything else on your system, without having to worry that whatever is running on the instance breaks, because if something is misconfigured, you just drop the instance and create a new one. So that's more or less the idea of containers. I don't know if it's clear, because I don't see your faces. Usually when we're all in a classroom, I can see if people is looking like, what is this guy talking about? I don't know if you are following well this. If nobody else says anything, I will continue. Yeah, perfect. Okay. If you have any questions, just ask. I mean, that's the good thing. So, okay, let's go to Spark. Let's go back to Spark. Imagine that we have this kind of environment, that we have our users and clients. We have some machines that we will dedicate them as master, and some machines that we will dedicate them as workers. So the master will be in charge of receiving the scripts to be executed, the Spark application, and the workers will be ready to receive what the master is telling them to execute and the data that they have to retrieve and run things. So at this time, we will use, for now, we will set up the full stack of client, masters, and workers in a single machine. This is my machine and the machines that you have at home. So we will do this first part in our machines. That remember that I told you in the instructions to try to install Singularity and to download the package that I prepared to you, that it has, let me show, it's here. It has the Singularity image, that it's the full environment. You see it's kind of big, the full environment, and we will play with this at this time, and later we will go with the Mare Nostrum, that it will be really distributed. Now we will distribute it, but at home, but in one machine, just to simulate that we have a very big cluster. So in the image of now don't worry, I will go step by step. and you will be able to follow me. We have one image of Spark, and we can start Spark as a client, as a master, or as a worker. Depending on how we tell it to start, it will give you a session for you to do some operations or to submit a Spark application. You can start it as a master, that you will tell, look, put here as a master and listen to some clients giving you applications and listen to workers arriving. Because when we can also start the container as a worker, and when we start as worker, we tell the worker, look, your master is over there. So when the worker starts, it connects to the master and tells, hey, I'm here and I'm available. So the master keeps a list of how many workers just started and are available. So what we will do now is to start this master node, 2 worker nodes, and a client session. As I said, we will use Singularity in this case. We have many. We have a few software for containerization. We have Docker, that's the most famous right now. But we also have Singularity. And Singularity, it's a little bit more simpler than Docker. And the idea that why we're using Singularity is because we're using a supercomputer. And with supercomputers, we have a problem, is that it's not a cloud, meaning that it's not like you go inside, you run whatever you want, you get root privileges because you need to install some drivers or to install some software or to access to some specific hardware. In the cloud, you can do it because you are in a virtualized environment or because you pay for machines as a service, infrastructure as a service. In a supercomputer, you have restricted access. You cannot just go inside and get root access or get privileged access. You have, we as the Mare Nostrum holders, we have to be careful of what is run inside of this. And you cannot just go inside and run whatever. You have to prepare your applications, tailor them, and running them into the system and see that no application will do any harm to the same machine, the other users, people outside the supercomputer. So it's a secure environment, the supercomputer. And Singularity was created, I think it was from a laboratory from MIT, or it was from around or MIT, or maybe it was from California. I can't recall now exactly who created it, but they created because they also had a supercomputer. They couldn't run Docker because Docker requires or can escalate privileges. And they said, okay, we need to do something similar, but that maintains always the privileges, that the user can run whatever they want, but they cannot escalate privileges. That is container, the execution of containers is contained in the application user space. And do not never try to access to the system space, let's say. And this works great for the Mare Nostrum, for example, because that's the case that we have. So we will also at home, we will run Singularity. Also for you, meaning that if we did this with Docker, most probably I would have to require you to modify permissions on your system, to give some permissions to your user that maybe you don't want to modify or that you cannot modify because the institution you are or the company in which you are, they don't allow you to do this. Virtual machines and Docker. So we go with Singularity, that once installed, you can run whatever you want because what you run will not have enough permissions to do bad things. And it works for what we want to do, it works great. Yeah, we don't want to do bad things. So we need to, well, to download the package that I indicated here. That's what I have here. That this is what, yeah, well, it's, that we need to download this. That this, what it has is the Spark image. This is an image of part of an, I think it was an Ubuntu system with Spark installed and configured. This is the descriptor of the image. Let me show you this because this is the receipt to cook the image. that here I'm telling, for example, to start like in Docker and other systems of containers, I'm telling, look, get this base here of singularity with R. I choose R because in the past I used R language, but don't worry, we will not use R unless you want. I tell it, look, be prepared to run Spark, be prepared to have the Spark environment, and be prepared to install Spark, meaning that I'm telling it that how to install Spark. So if you don't like this image that I gave to you, and you want to modify or add things, if you think that the image is good, but you would like to have other software installed, you can go here. You can add it here in your zip, telling Singularity, look, I want more things on my image, and then build the image again. So you will have your version of the image with this new software. Also, you can create your own image, telling to get this as base. So it will be like, okay, get as base this image, and now add more things to this. That's the good thing of containers, that you can create versions and additions in a very easy way. In the package, we also will see some examples that we will run in Mare Nostrum, some data sets. I think that the linkage, you don't have it because I removed it, because we will do everything with this data set. We also will have some novels as data set and some data as example, and the script that we will go through later with the step-by-step to run things on Mare Nostrum. This is the script that sets up the environment, and run everything in the system in an automatic way. So here in the different files, you can start opening terminals and going where you downloaded this package of files in order to run them, and let's go following them. So the image of Spark I prepared with, as I show you here, to say, okay, you can run Spark with a parameter, and this parameter can be three kinds of parameters. It can be as a console interface, as a master, or as a worker. In that, remember this structure here, we will use the same image, but for each one we will tell it how to start. So we will prepare, first of all, we need to prepare the environment. And let me see how to do this without changing no. I want to select, and I don't know if Adobe Reader is letting me to select this. Let me do one thing. No. Let me try. This is technical problems. Well, technical problems. It's more like I want to run this. Run this in a way. Let me check where I had it. Not to go typing this everything. Give me just a brief second for this. Just to check if I already saved in a text file. Oh wait, maybe I can do it from the PowerPoint that I created this. I will copy it into a text file and copy it to you in the chat, so you don't have to go and copying this line by line that you have. Let me arrange it just for a moment. Okay. So where's the chat? I want to know where's the chat. Here. Okay, I will dump loads of code. I hope that it starts. It is well copied. Okay, in the chat you will see a lot of things. Beware with the jump lines. Let's prepare the environment. So, and we will see now. First of all, we have to tell it which image we will use. Okay, we will use this is Spark. That's fine. We will tell that the host manager will be localhost. At this time, we need to know where the host will be placed. So it will be localhost at this time. More things that we need to do. We will tell where the output will be. The good thing is that for each master and for each worker, we will have an output file to know that everything went well, or just to see the logs, or to see if there was an error, or it's a log file of the execution. So I think that we will have in this case 3 things going at the same time, the master and the 2 workers, just to keep them controlled. And also we will give Spark a temporary directory just to save temporary files and temporary information. This for each worker and for each master will be, in this case, their temporary place from their machines. So it's not that they will share things through the temp. It's just for every worker and master to have some space to store some data for themselves. Okay. Also, let's create this directory just to have it in case that we don't have. Okay. Next thing is that we will tell it what the Spark worker will use. And by here, we dimension the worker. We tell Spark how many CPUs we want and how much memory we will use for them, for each one of the workers. In this case, for example, I told that every worker will use 1 CPU and 700 more or less megabytes of RAM memory. I could also give 1 gigabyte, 2 gigabytes, 10 gigabytes. The only thing that we have to think about is that we can the sum of all the workers cannot exceed the amount of memory that we have in the machine. Technically, we tell each worker to get as much memory as they want, and a Linux system or a Unix system will give them virtual memory, and they will say, okay, you want a terabyte of RAM, that's okay, I don't have it, but I will start swapping memory when you don't look, swapping memory from memory to disk. Also, what happens is that if each worker thinks that they have lots of memory, but this memory is overlapped with other workers, they will start kicking the crap out of them. They will start competing for memory. So instead of parallelism, what we will have is processes fighting to have a piece of memory. So when we dimension our Spark cluster, we have to see how many workers we create in each working machine, physical machine, and how much memory we give to them. So let's start doing things. Let's start running things. Just an advice with the slash. See that in the instructions. The instructions have a slash. You can remove and join with the bottom line. So, for example, here, just to avoid problems with tabulators, because when copying these lines into the chat, I don't know if the chat will transform the tabulators into spaces or will understand the break lines as a break line with a tabulator or a space. Copy them to a notepad or a Gadget or whichever editor you have, and join the lines that have the full line slash and then continue below. Join them just to avoid problems. So I want to see the chat again. I'm hiding it, and it insists on here. Here's the chat. So what we're running here, Singularity, we are telling to run the image that we had, to create an instance of this image, run it as a master. The host will be the machine we're running in, and we tell the output to be in these machines, in these files, the out.out and .app. We run it, and now we have the master running. Now the master cannot execute anything because it does not have any worker. So the next thing that we need is to create some worker. let me fix the line and okay. So we will start a worker again. Create an instance, another instance of our image of Spark, but as a worker, we give the Spark temporary space. We give the arguments, the parameters to know how much CPU and memory the worker is able to use. We tell it where is the master, because when starting this, it will communicate our started master that, hey, I'm here and I am available for running instructions, running and processing data. We tell with this syntax that Spark // the host master and the port 7077. This is the port that the master uses to listen for workers arriving. We run this and now we have a worker. Now we need a second worker that we will create a second worker again with a different, in this case, with a different output just to differentiate worker 1 and worker 2. And now we have our cluster set up. Now, the thing is that if we do some kind of grep, we go for ps grep Spark, we see that aside of the grep line, we have our, let's see if it, oh yeah, the master, we have a process running as master, and we have two processes running as workers, and they are connected. I think that if we do the following, let's do a tail of the master out. Nothing. Okay. In the air, it tells you, hey, look what happened here. I received two workers. Well, first it tells I'm the only master. Another thing interesting is that I told you one master and several workers, but we can put more masters in case that we have lots of petitions and we want to load balance the amount of clients that we receive to our cluster. So basically, this master says, I'm the only master, so I must be the leader master. I'm alive, and I received two workers from this IP, and I opened this port for them to talk to them with one core and this amount of RAM. So now our cluster is ready to work. Also, it started a web UI. I cannot open it here because I'm connected SSH to a cluster, but if you're at home, I think that you can start something like this with localhost, and you will see the interface of Spark to see things go. It's a curiosity that sometimes you want to check things through here. Okay, next, let's continue. Let me show again. Every time that I switch things, I lose the chat. Now I have here back the chat. So also, not to run now, but you could kill the environment just by killing the processes of Spark. To do a grep, get their PIDs, and then kill them. This is the bad way of doing it. I tell you, we are killing it -9. Spark should be prepared to receive a kill -15 to tell the work. First of all, tell the workers, please stop. The workers will close themselves. They will unregister from the master, so the master will know that workers are going off. And finally, you shut down the master with a kill -15. As they are in containers, if you kill them abruptly with a kill -9, you will not cause any damage unless they are running data and storing data, obviously. But if the cluster is idle, as they are in containers, you can destroy them without any consequence, because remember, the container is not persistent. It's created to be instanced and then dropped to the trash. So here we don't have the problem of shutting down gracefully and slowly the cluster. But if you run this in a persistent environment, please stop things politely here. So let's see what we can do. So I guess that everybody more or less you can you have been able to start your cluster and see that things are running. What can we do now? So we can run Spark shell. Spark shell is a shell of Spark, obviously, in Scala. But we also have available Spark R to run in R language, or RCran, and also in Python. For this, we will be using Scala because I myself, I like to use R. I like to use R to code analytics, big data operations, and machine learning, etc. But most of the people told me, oh, but we are not fans of R, we like Python. So to be in the middle, I decided to use it in Scala, to do it in Scala. Also, we learn a little bit of a new language in case that you're not used to Scala. It's not difficult. If you know programming, you will be you will learn it easy. Also, we will go step by step, and you will see the small things of everything. What we do now? So we need to run this instance, an instance as a client. Let me. Oh, first of all, let me copy in the chat the function to kill. Oh, I put the function here. I'm putting this, but this, remember, this is not to write this. This is the system symbol. This is this. Okay, for you not to write this with the dollar sign at the beginning and saying, oh, it is not working. I copy here this, and also I will copy in the chat the instruction to start the client. And now we start the client. No, does not want to copy. Maybe now. Okay, see that now we are executing. We're using execute because instead of running a daemon or running the instance just as something to keep going, we want something that we start, we have some interaction, and when we close it, the container will close. We don't need to kill this session. That's why for this container, instead of run an instance of the image, we're just telling, look, create an instance and execute this. And once I finish this execution, when I log off of this execution, just kill the container. I don't need it anymore. By the way, you're seeing well the screen, right? You're reading everything that's on the terminal. Okay. See, you're seeing what I'm copying into the black screen. Okay, good. Just to see that. Okay. So we are now in a Spark session. Well, we have here the Scala terminal telling us, okay, you are able to run commands. For here, we run an interactive session, but if instead of just running this session like this, I would have put as an input with a pipe, I would have piped some Scala script, some file with a Scala script, it would have executed. It's like a bash, well, it's a shell terminal at the end. So instead of, if you don't want to have things interactively, you just write them in a notepad, like we will in a text file, as we will do later with Mare Nostrum, and just submit this file to be executed. Okay, so we are now here. So everyone, I hope that everyone has the running and everything is working well. In your homes, if you are running things, this and you reach the Scala console. If I'm going too quick, just tell me, and I will try to go slower. Maybe I know that I'm familiar with copying and putting things here in that way, but maybe people is trying to figure out something. Just tell me. For this, okay, can your slide downloading? Oh, if you couldn't download it, let me copy it to you again. I'm also copying in the chat for everyone to have it. let me see if I'm copying it well. I think it's correctly copied. I 3x a m h 2p. Okay, so here is where you have the. It's around 600 megabytes. So depending on your connection, I hope you have a decently quick connection. It will take a few moments. If not, it will take a little bit. Okay, so also, if you're downloading things, let me copy another link that it will come later. Let me find and copy to you, because we will have a data set that if you didn't copy from the instructions, it's in the instructions, meaning that if you already downloaded it when executing the instructions, this other link, you already have it. Could you? Could you upload the yes. I could have done this from the beginning, so you could follow them and then copy. Oh, I'm a disaster. Sorry. Let me copy Dropbox link. It's in Dropbox. Okay, so from this you can download the slides. And so instead of writing things or me copying things into the chat, you can copy and paste directly from the slides. Just an important thing is that PDF and Office and everything tend to change characters, meaning that sometimes I write a dash and it stores it as a stylish dash that looks like a dash, but it's not a dash. And if you do a copy and paste into the terminal will say unknown Unicode symbol. So when copying and pasting things from the slides, beware with dashes, beware with jump lines, and beware with I think that's it. The dashes are the main problem. If you run some instruction and it gives you an error of weird code or weird symbol or whatever, check the line, see that the dash is correct, or write the dash from the console to be sure that the code is okay. Okay, so let me go to where we were. We were here in Spark and Scala. Do you want a couple of minutes to run to be in front of this console? Or maybe I can continue and the ones that everyone will catch up. Okay. Okay. I hope that you will catch up quick. Not a problem. Let's go for Spark and Scala and SQL. So we are now in a Scala session, and we are connected. Maybe I can do a thing instead of being changing screen. Maybe, well, you can see both things, right? Yeah. It has the problems that it does these kind of things and it's ugly, but yeah. Okay, so now we see both things, and I'm not jumping from one to the other. So now we're connected to the master node. See that here when connecting, it said, look, the master. Oh, by the way, if you want to exit, 2.q. And then as we can start again and connect to the master. I cannot download. Oh, you cannot download the forbidden. Let me check. Let me check. The host. Did everyone else could download the CSV host file? Okay, maybe it's just a problem now. Try again this without the wget, just in case that there's something weird. Oh, I can now. Maybe it was some miscopied character. Okay, perfect. Good. Okay, so Let's see things for starting with Scala. It's a language, it's a scripting language, but you can also program objects, and it's oriented to more, how to say it, it's a functional or even descriptive programming, meaning that it's not imperative, it's not like other languages that you tell when this condition, loop for here, if, else, etc. It's more like, I want this to happen, run, and you tell what you want to happen. We can also create variables, and we can also create if else, but is not the best way to run things on Scala. Also, when dealing with data analytics, it's not, it's instead of even in Scala or other languages, you don't do if else or loops over data. You usually set up a filter over data or select over data, or you apply something over data. That's what Scala is prepared for. So we have variables and values. For example, we can create a value. A value is something that will be static, meaning that A will be hello, and you don't expect A to change. We can change it, but the thing is that Spark and Scala are programmed to understand that, okay, A will not change, so I will treat as something that will not change. If we want variables to change, we do, instead of values, variables. And then to variables, we can change them. I think that we can change A, even if it's a value. No, it's telling me at this version, it is already telling me, no, you cannot change this. You have to, it's a value. It's not a variable. It's stored this as something that will be constant. And then we can ask also for B, also for A. And for Spark, there's the basic bricks are called resilient distributed data sets. So the operations that Spark does and how it distributes it is something that's called RDD. And everything in Spark is an RDD. Over RDDs, we have DDFs, distributed data frames. The thing is that over RDDs, we can create new functions. We can create what I will show you now as Mapreduce. That's how we will program, or we will be able to program distributed operations. And over FFD, DDFs, we will be able to apply aggregation functions and analytic functions. All the functions for DDFs are programmed as treating them as RDDs. And if you don't find your function for data frames, distributed data frames, you can code them in a lower level as RDDs. For now, you don't have to worry about that. I think that I didn't do an example at very low level because almost everything that we will do we will be able to do this as DDFs. Again, exit to .skew. For people here, exit, this will not work, or by, this will not work. You have to do to .skew. So what I'm talking about, Mapreduce. Mapreduce is a low-level way of distributing operations. Basically, imagine that we have some data and we want to apply some operation to this data. And this operation, we know that it will be, in the easiest scenario, it will be the same operation to every element of data. Or maybe it's something more complex, but we can divide it into applying the same operations over each piece of data. So one of the things that we can do to parallelize is we split this data in different subsets of data. Then we apply a function over this. I'm saying apply because apply is the keyword in R. This is basically in Scala or in Python, we also call it map, meaning that we are telling that over each piece of data, we are applying a function, saying that for it's, if you are familiar with the lambda functions, same idea. We apply for every element on our sets, we apply a function. And then we get the results for each subset. And the last step is the reduce. We mapped a function over a set of data, and now we have to reduce all the results to get the final results. And we can tell, look, for every 2 or more elements in the result, let's merge it this way. And we give the functions of mapping, the function that we want to apply over our data, and we give the function to join or to aggregate results. So this is the Mapreduce schema. First, we parallelize data, we split data, we tell what to do for each element in each data shard. We could apply it directly to data. We do not need to split, but if we have several machines, several processes, we split them. And finally, we reduce it, so we rejoin the results. And most of the Spark operations have Mapreduce operations implemented inside. We will not be aware of them, meaning that we will work in high level, in a high level of operating. We will have functions of select, filter, addition, etc., grouping, etc. But if there's a function that is not available, we can always go to low level and with Mapreduce functions compose our analytics function for our data. Does the reduce cause SQL aggregation? What do you mean cause? The reduce, if we were in SQL, so imagine that this is a database from an SQL database. What if we split a table into subtables? We applied we made some selects were indexed from 1 to, or index from 1 to 10, 11 to 20, 21 to 30. We have our table split. We for each one we apply an operation, and later we do an aggregation, saying that putting all the table together, all the results together, aggregate. That would be a way to do this, meaning that but this goes far beyond. In SQL aggregation, you aggregate and you can get aggregation operations like sum, maximum, count, more complex functions, UDF functions by a kind, or we can aggregate in general. Imagine that here in this reduce, we are counting words. This is the classic example that we will do with Mare Nostrum. Imagine that we have the novel Moby Dick that we have in the files, and we want to count the number of times every word appears in the book. So one thing that we can do is we split data, or even if we don't split data, we tell to the book, to the file with all the words, is count, put a counter on each word, counter of 1. This would be the map. We are telling to each word 1, value 1. And now when you reduce by the same word and add their number. So if we have hello with a 1 and hello with a 1, when reducing, it will reduce, 2 hellos. Let's reduce it to 1 hello, and let's add the 1 and 1, 2. Now I have 2 hellos. Oh, here's a third hello with a 1. Now I have 3 hellos. And this would be similar to aggregations, group bys in SQL and other operations. We can reduce in many things. We can put the function we want to reduce, but it would be an easy way to understand this. Okay, another question. I have seen aggregation as a metric. Checking it. So what's checking is that it's part of reduce or not reduce. Okay. I don't have the interface right now, so I can't because I cannot access to the full interface to see what is showing. Usually in the interface, what I expect to appear also is the number of maps and reduces, because internally Spark, each map and each reduce is a process, is a stage of processing data, and sometimes to also it comes from Hadoop. Hadoop was based in Mapreduce and Spark inherited it. And one of the metric to evaluate how the system is doing is counting the number of maps and reduces that you do in low level, to know if you need more workers of one kind, workers of other kind. Often, if you map things, you will need not much memory if you, or lots of memory if you have big data, very big data, or less memory if you are just mapping elements to each element on data. And if you have a reduce that's really complex or has to collect lots of data, instead of just aggregating this, is just collecting them, you can evaluate, maybe I need more workers to reduce, or I need more workers to map. Internally, you can modify these things. Now, in the surface level, we just create workers. But we can tinker with this kind of platforms to tell how many maps and reduces we need. The thing is that I'm sorry, Juanma, but I don't have. If I try to access here, I think that it will not be much possible because I'm in a tunnel, SSH tunnel. So okay, good. So we have this. This is how it works inside. And the good thing is that every shard of data can be sent to a different worker, and every worker just deals with its shard of data. I think I didn't put it here, but just to comment that there are some operations that are not as simple as this. It's not just like a map and reduce. They need to exchange data. Imagine that this reduce operation or this mapping operation requires data to cross data from other shards. There's a thing called shuffling. That means that between the map and the reduce, the system must stop processing data to exchange pieces of data in order to continue. This is something that might happen, and when checking the development of the pipeline or the execution of your Spark job, you will see maps, reduces, and sometimes shuffling. And you see that everything stops at shuffling and start shuffling. That this means that the different workers will start exchanging data. Imagine, for example, for the word count, you don't need to shuffle anything. I just put a number on every word and start adding numbers by joining words that are the same. It's a map, and then start reducing and reducing and reducing. But for example, imagine that you have a machine learning algorithm that requires to cross data, that maybe to do some cross validation, or maybe you have a neural network that requires that for all the inputs to pass through all the neurons and then provide all the outputs. If you split it in this way and you have different batches, you have a big batch and you have to split it, at some point data will have to be exchanged between workers. Usually the algorithms for Spark are optimized to reduce this as much as possible, or they are crafted in order to avoid shuffling, maybe with approximated algorithms. This is something that we will quickly see, or I will quickly explain when we go through Spark ML. But this map and reduce schema has this extra thing that, depending on the operation that you want to do, here in the middle, you will have a crossing point where the system needs to cross data and to do another map or another reduce while crossing data. This is part of designing your application and observing your system in case that you need to attend this shuffling or improve the network between the computing machines, or to modify the algorithm to prevent this. The ones that you're, if you're familiar with SQL, remember that when doing a big query in which you're selecting and aggregating data, it's not the same. Or when you're joining data, you're joining two tables, it's not the same. For example, doing an aggregation before the joining, that aggregating before the joining. In one, we can have lots of crossings of entries into the table before aggregating or removing the ones that are not needed. And in the other one, you're cutting corners. This is a metaphor of what could happen when you process things distributedly, that you're at some point you need to filter things before doing some operation to avoid crossing things, or sometimes you cannot avoid it. Then you assume it unfortunately. But this will happen when you create more complex Spark operations. You don't have to worry right now of this. This is a step of optimization. I just wanted for you to know that this can happen. So let's go to the thing. We are inside here a Spark session. This is the Spark session. Text. Okay. For some reason, select all. Aha. So one thing that we will do. Oh, here North 3. This address is from Nostrum, I think, because it will tell me, it will tell us to shut up. Well, it will not, but for one reason. Spark is lazy. This means that I just told Spark to read a file and parallelize it. SC is the Spark context. That means that everything that we load here will be automatically parallelized. Is this step here, the parallelize step. Then we have text file, and it tells you, oh yes, it's an RDD, like everything Spark, that points to this file. Well, that's okay. But what happens if we try to access this? If we want to get the first, let's see what happens. Oh, yeah, it will work. Okay, it will work because I included this in the container. I was waiting now for this to explode. Oh, this is interesting. Has not accepted any resources. Check that workers are registered and have sufficient resources. See what happens here. This didn't happen before. Let's see if there's any problem with this. I will have to cancel, unfortunately. Okay, what might happen here? It's telling us, warning, there are no resources. Check that the workers are registered. Whoa, this means that maybe something happened. Let's check it. Grep Spark. So I will do it big just to see it. They seem to be working. My question is, why? Oh, somebody activated the microphone, I guess. So it has the workers. It seems to be, they seem to be registered, because remember that we checked the master out. Oh, registering the Spark shell. Wait, somebody has the microphone activated, and okay. Okay. Do we need to load some models? No, not yet, because the thing that we are trying to execute is just something really simple. Technically, if this is working, singularly Spark, this, let me check again. Command not found. Yes. Okay, Spark. Spark. What was the name? This is it. No. Okay. Image. Let's start. Wait. What I'm doing wrong? That's Spark shell. Oh, yeah. I was trying to introduce here the image. Okay, I'm creating a Spark shell, connecting to the master. That's here. Because it was complaining that it didn't find the resources. It didn't find the, workers. if I tell it now, for this, Singularity command, remove the dollar in the front, just in case it is this. Because from here, select this one, select from here, not try to remove the dollar in the front. The dollar is the command line. Let's see first. This what is showing here is that it's trying to allocate things in the it's doing this split of data and trying to allocate to workers, and it's failing because it's telling me that it is not finding any workers, but we know that we have workers. Okay. Okay, we have enough CPU, we have memory. Let's try to figure out what's happening right now, because this is the kind of things that yesterday it worked and suddenly it does not work for some reason. If not, let me try one thing. Let me try to kill and redo this again, just to try to identify. Because this no es possible, this is not. Why are you doing this to me right now? Singularity. For Singularity, let's see what. Let's try to remove it. For do this. Let me copy and paste. Remove the put everything in the same line, meaning that. So as Elias is telling you, put everything in the same line. This is for yet. Okay, let's out. Oh, wait. Let me connect again, just to see what's happening. Let's enter into the ACM. Let's see, nobody else is in here. I have the image. Grep, no, so how can grep not be installed in this machine? The thing is that I did it in a machine with Ubuntu, and this has CentOS. So probably I need to install grep. How CentOS does not bring grep? Even less group. No grep, it has grep.
I believe you're missing a slash before the B in the last command.
Okay. Perfect. Okay, thank you. Thank you. So, okay, we have this, and if we do some this in order to get these, and we kill them to finish all of this. Okay, let me copy this to you in case that you want to finish No, it's not for Luca. It's not a VM. We are not in a VM. We are in the real deal here. I killed everything right now. Let's go and let's copy. Let's see first of all that this copied well, just in case the work. Okay, yeah, it's PDFs are not friend of work well done. Just in case, just to see that the workers are working properly. Let's run the Singularity Images Master. First, maybe I will remove the okay, it does not accept tabs. Oh, it's not. Yes, because I didn't. I closed the terminal again. Okay, let's set up the environment. Can something in Spark here? Let's go to the Spark master. Dollar master out. .r. Okay. Let's analyze it. So here we registered the two workers. We registered the app Spark shell. This is the console. The request of the console, and then we closed it because I closed it. Got dissociated, and also this. Then we registered again the app. Then we removed the app again, and then we start again. But see that the workers never disappeared. That's the weird thing. Let's do something. Let's give it more memory, just in case. It should not be this the problem, but let's give more memory to the workers. No, I will give 1 gigabyte, just in case. And I will do another thing, that I will rewrite the dashes to ensure that we don't have any weird value here. Then let's start again the master. Okay, we have a master running. Let's run one worker. And the second worker. Okay. Let's see what's in the master error. Okay. Well, this is the cut. It started it again. It started. Disabled. Okay, everything okay. And we have two workers. Now let's try to go to the terminal, to the session. Well, I think it was in one line here. And let's try to see that it is, this is well copied. Okay, we're connecting to the Spark shell. See the dash thing, that it eats the dashes. And now we have to go checking that everything's okay. Okay, let's start Spark. Let's see if it connects. I don't like this. It should tell here my host master, not not this one. What? No. What happened here? Master. Dash master. See, it's the dashes. It's driving us crazy. Okay, we're connecting. So let me copy it again in the chat. See that this is a kind of practical session that we all have to manage how to solve all of this. Okay, now it's connected to the host. Okay, now let's, if I say Spark context, it tells me yes, I'm the Spark context. If I ask it, let me arrange this here. If I tell it read this file that I'm copying right now, is writing down that he has to read the file. Then if I do text file first open and close brackets, okay, first text file first. I mean, what if I tell you first? Oh, it's already working. What happened? I don't know. Maybe it's some copy and paste of these dashes that made the session not available. This is kind of the magic of running Spark, and also the magic of the demo effect. Everyone could work it here. Yes, might not working. Not working yet. Let's do something. Let me copy exactly. Not working too, Stefano? Okay, first of all, kill Spark. Kill everything that contains Spark. Because I'm copying here the same instructions. Yeah, please give more resources for the workers. So give 1 GB. Maybe it was that for some reason Spark consumed everything. So do something like this before starting the workers. Because this is really weird, meaning that this example should not be consuming 700 megabytes. When I ran it the other day, it worked well like this. It is weird, at least for me, that just adding a little bit more memory happens to be the game changing. It is possible that for some reason, when rebuilding the image, the Spark version changed, but I'm using a stable one. See that I'm using the version 2.4 when the newest one is the 3rd. So, okay, everyone give 1 GB. If it's working, maybe it's the Java version that suddenly it allocates memory differently. It's the things that deserves to be researched. What happened for this version to require this extra memory? Yeah. Did you install Singularity first of all? Yeah. Oh, thanks, Elias, for copying and pasting everything. So people follow the Elias post. Okay, so let's go with 1 GB. Reading a file, that's almost nothing. It takes 1 GB per worker. Let's congratulate the system. Maybe it's just it's not that it occupies 1 GB, but it tries to allocate the minimum amount of memory. Now it's 1 GB. Time ago it was 256 megabytes. Maybe they changed it, but it's weird. I must tell you that in a previous session of this course, they just changed one small detail of Java between the day that I tried it and the day of the session, and we were all crazy trying to figure out that Java 1.8.0.100, it was not the same as 200. So yeah, I'm worried for you. Could you start Singularity or get something from me? Did you install it and had it correctly installed? Not a problem. Go. You can. Oh, okay. You can install it now, and here you get the Elias is posting the startup, so you can copy all together, and do not worry for oh, your microphone is not. Oh, dang it. Okay, so it seems that now with 1 GB per worker, things are working. Okay, so we will work with that. 1 GB is not too much nowadays. When we started this course, it was kind of a thing, 1 GB, but luckily today's machines have at least 4 GB. I think that when we started this, my machine had 2 GB of RAM, so 2 workers would have overwhelmed everything. Imagine how old was my machine at that time. Okay, well, yeah, keep trying, check if Singularity is response, because it's the basic. When Singularity works, everything will work technically, because Singularity is everything is executed inside the container of Singularity. So Singularity is the manager that when it starts, you will have the same version of the container as everyone else. Okay, well, if you can catch up, let's try to catch up while we're continuing. Okay, so what do we have here next? What do we have next? We have the Spark session working. We know that it works and it gets the first. What does this mean? That even with parentheses or without, it's implemented with both, but it gives us the first thing. What happened with this text file? Actually, that's where I loaded the file. It's actually an RDD, and it's let's say an instruction, a Mapreduce instruction that Spark wrote down in the notepad in order to be executed. But when we do this here, when we tell it to read, Spark does not read anything yet because it's lazy. Spark just says, okay, I know that you want to read something. I'm writing it down, and I will only execute this once you need it, once you tell me to do something with the data inside of this file. So if I write this, but I start working with other variables, other files, etc., this text file will never be executed. Spark has it just in case that we tell it to do something with it, but it will not be read and paralyze it. It knows that this text file points to this README file. But it's when I tell it, give me the first element, the first line, first is give me the first line, then it Spark starts working and starts sending things to the workers to do. In this case, it sends to the workers, please read this file and give me the first line you find. That then it starts executing things. So if you write a very complex script, but there are things that are never executed, Spark will not execute them. And Spark will only execute them when needed. And this allows Spark to organize and schedule to orchestrate the pipeline to see what is needed, when it is needed, and where it is needed. That's the advantage of platforms like Spark, that they schedule things only when needed. So if we read the first thing, then it executes things. and also we can put into a variable. And then now we have this computed. It's Spark does not need to compute it again. It already has not only in catch, if we set available in the options of Spark to have catch, but we have now it in our session. Now it's down our session. We have to differentiate in Spark things that are in a disk, things that are up in Spark, that means that they are ready to be executed in memory or waiting to be executed in memory, and things that are in our terminal, means that we have them collected. For example, first is a collecting function. We have the first is collecting function. We can take is also a collecting function. If I write take 5, it gives me an array of 5 lines. Also collect, that I will not execute, but if I did something like this, I would collect everything in the file and put in a local file, in a file in my session, in the master. So I would be collecting things from the file to the master. If I do not collect anything, just point to the file. What I'm saying is to Spark, look, you don't need to have everything one point in collected in the master. Just access it whenever you need. And if I collect something, even that, I decide to collect something, and I want to process it again with Spark, I need Spark to parallelize it again, because I collected everything and I need to spread it again. Here, this function with text file already parallelizes it, but also the function parallelize from the Spark context allows you to transform a collected or local variable and parallelize it. Imagine that instead of reading this file with Spark, you have a CSV file locally. You could read it and parallelize by hand, or use this function to say read and parallelize, and then you read in between quotes because you're not reading at the time, but you're telling Spark, when I need this file, I want you to read it, parallelize it, and then process it and give me whatever I asked. Yeah. This comment goes from Jay in case that he has some issues with SSH. It could be. So you understand the idea of having things collected and having things lazy on Spark, right? You see the point, right? Because sometimes imagine that I will do a thing wrong. I will read file that does not exist. Spark is telling me, okay, you want this file, I will create a pointer, I will create an object, an RDD in the Spark space that points to the file. But this file does not exist. It does not complain because until I need something from this, it will not complain. When I tell, give me something from this AAA, then it will try to execute, Spark will try to execute this, telling the workers, go to this AAA file and do this and get the first. And then when the workers will return an exception, hey, this does not exist. What happens here? And it's then when I will get the error. Just for you to know that if there's a mistake in your Spark code, but it is syntactically correct or semantically correct if you use objects, it will not complain until it will not give you an exception until you try to collect things. You will introduce them into the console, or the script will arrive to this point of the line, but it will not complain at that point because it is not executing anything until you take or collect or do some operation that you want to retrieve. Like, for example, storing things or printing things in console is also a taking operation, a collecting operation. Let's do the word count. This is I'll try to be quick because I want to catch up the time we lost with all this trouble. So we have text file. I can get the first one, text file first, and get the first element, the first line. That happens to be the README of Spark. So it starts with Apache Spark. But I want to count the words. What can I do? I can do this. Let me see if it's well copied. It is not, so I will complete it. What I'm doing here a Mapreduce thing. This is low level. This is don't worry, this is the only low level that we will see. But for you to understand, I told create me a variable text flat map, because a text file has spaces, but has break lines, etc. I'm telling just if you find a space or a jump, just put it into the same bag. Read from the text file. From the text file, create me a flat map. So this is a mapping operation, and for each line, split it in spaces. Basically, I'm telling it for every line that you find, split this line into spaces. So give me the words and put them into the same bag. And Spark says, okay, well, I created this text flat map, but not executed yet. Next thing, in this text flat map, what I have is a bag of words. Right at the end, I collected the words, everything that's separated by a space. Next thing is telling, okay, from create me words, and from this bag of words, apply this function. That's for every word. This is the map. Is apply this function to every word in my bag of words. Create a tuple of the same word and one, meaning that you've seen this word one time. Oh, yeah. You're connecting to the supercomputer. Don't yet. We are not in the supercomputer. We're at home. We are doing the stuff at home. We will later. I will tell you to connect to the supercomputer. You can execute anything because you're connecting to the login node that's prepared and secured for you to run nothing. So this you have to do this at home at this time. We will go later to the supercomputing. So that's the thing. That's the problem. You have to do this part is still at home. We're experimenting at home. Later we will go with the supercomputer. Do not worry for that. Okay, so let's go back to the bag of words. I read a file. I split every line by spaces, getting the words and putting in the same bag. And I'm telling that for every word exists, for every word even repeated, for every word in the bag, giving a label called number one. So I will have now every word appearing in the file with a one. And now this was the map. Now I will reduce. I will tell it, look, I want that from the words. I want to reduce. Oh, it is copy. See that it is copying and pasting it wrong. Check when you copy and paste. Check it twice, that you don't introduce any error. So for every word, for every tuple of word plus the number one, I'm telling it reduce by key. This meaning aggregate for each couple of matching words, add their numbers. For every same key, add their values. So what will it do? From all the tuples with a word and the number one, it will start matching two tuples that match the same word and adding the number, and then putting back into the bag. So it removes the aggregated ones and reintroduces to the bag. And this is done repeatedly until there are no more matching words, meaning that at the end we will have a tuples of unique words with the total sum of times that word happened in the file. So this is as simple as this. If I tell counts, that counts is an RDD object. It is not yet executed because I didn't tell it to print anything or to collect anything. If I tell it take 5, now Spark will start working and it will return me a tuple of, well, in this case, the word package appears once, this appears once, integration once, Python appears 2, and this kind of URL appears 1. Let me do a for each print. For each print line, it is for putting it pretty. It prints 5 randomly taken from this operation. But I want to sort it because I could take more. I could take 10 and I would have 10. Look, the word general appears 3 times. Maybe I want to sort it. So maybe I can do, well, ranking. I can create a ranking. Counts. I can do a sort by. Sort by. And what I tell by sort by, for every element, sort by its second value, because this is the first value, this is the second value, this is the first value, this is the second value. So I'm telling for every tuple, order by the second value, and false meaning that I want it ascending, not descending. And if I check at the ranking, I could do ranking and do take 5 again for each print line. Okay, I have the first ones collected. Right here, this happens because we have at some point of the file there are double spaces, and when I split it by space, it uses the space, the additional space, as well between 2 spaces. There's 0 length word, and this happens 72 times. That's why happened this here. But we see, for example, that the word D appears 23 times, 2 appears 17, Spark 15, etc. Let's collect the other results, because here I only took 5. Let's do, I create bar local result, and from the ranking, I tell it to collect. This means that everything that you have processed, if you have not processed it, do it now and bring it back together to my local session here. So I can process it now with other things. So now we have all the local results. And for example, I could do the local result for each print line. And I'm printing from all the words ordered by ranking. I have the ranking of collected words. So I did this word count just with, let's say, Mapreduce operations that are these operations like this one. More things that we could do, we could filter. For example, here, let's hope that it copies well. No, it didn't. Here, what I'm saying is from the counts, filter them, and for every element, so for every element X, check that it is not equal to the 0 length word. That's the 72 thing that happens 72 times. If it's equals, if this element, so if the first element, the word, is equals to, no, sorry. If the first element is equal to the void word or the empty word not, then filter it, meaning that keep it. Filter refers to keep it, the one that accomplishes this condition. So if I do this, and then I sort it out again because I got from the count, okay, and I collect it again, but now without by having filtered this, collect. If I do the print, I will see that this is not for each. It's terrible, this copy and paste from PDF. Also, I don't know if Windows is responsible for this. See, we don't have the take 5. Oh. Oh, I see what happened. It copied wrong here. Sorry. It's like this. Okay. Clean rank. I repeat the operation. Not a problem. From clear rank, I will collect it. And I will take 5 to print. And now I have the ranking again. This is just the first 5 ones without that thing that happened here of the empty word, that it collected this. We've just filtered it with a Mapreduce operation. It works. Perfect. Then maybe it's my fault that I'm using the Linux subsystem for Windows, and maybe the clipboard of Windows is kind of crazy. If it works for you, perfect. You don't have to worry about this. Just to be diligent, to be observing in case that something weird happens. So we have Mapreduce operations. It is clear for you what happened? Could you work it and see how it works? Okay, so why I showed you this that seems kind of complex and can get even more complex, because this is the low operations way of working with Spark, that in case that the next functions that I will show you that are more high level, in case that your functions are not in the high level functions, you can always craft your own operation, your own algorithm, function, etc., with this kind of low level operations, meaning that you get data, you tell it for each element of data what to do with it, and when you have it processed, every element of data, how to aggregate or collect it again, how to put all the results together. We will see that something as simple as this word count can be easily done with a SQL-like group by. But I wanted you to see that that there's this low level of operations in case that you don't find your operation available in the standard libraries, or that it is extremely complex if you do the other ways. Okay, let's go for Spark SQL. The thing is that Spark, aside of working with RDDs, works with FFDs, distributed data frames. That's a higher level of abstraction that that you can use and start using things like select, filter, group, limit operations that, if you are familiar with SQL, it will be you will know them directly. So let me show you very briefly the Spark SQL, and then we make a coffee break, okay? Because it's already 4. It's half the time. Let me finish with this, and then it will be quick, and then we do 15 minutes of coffee break, okay? It's good. So we have RDDs that look awfully complex to craft these kind of things. They can be changed, and you can create incredible functions with this. But when we have data, we like to manage things easily. So one of the things that Spark allows us is to do things as relational databases. Example, Spark, SQL. So data can be treated as distributed data frame, as a data frame, as a table. For if you are not used to the word data frame, imagine a multi-dimensional table that usually you can treat it as a table. And you can do slicing. This means selecting, doing conditions, this is filtering, grouping, and also do map reducing operations, because behind the DDFs, we have RDDs. We can do map and reduce. So we get the data set of the whose data set, right? I already uncompressed it, but look, let me exit now. But if you uncompress it, we have here this CSV. We will be using this CSV, the A. This is the, I think it's the Boston housing or the Houston housing. or the Housing USA. No, Housing USA, sorry. It's a data set with data of housing information in the United States, I think. Data set A and data set B. And we will use just as an example of big data, something that when we do some operations, we will see that Spark takes some time to process everything, not like with the word count that we did, that it took milliseconds. So everyone uncompress this data and have it ready, because we will be loading this schema here. So once we have it uncompressed, we will open a session of Spark, and I will have to correct this again to avoid all the problems. I create again a Spark session, and I will tell it, instead of read text, do the text file operation. What I will do, this is a same line, just for you to know. Use a notepad or something to put them together, or you can I'm trying to copy and paste, and Windows is giving me a hard time to have it well copied and pasted, but we will accomplish it. So have this as just a line. And what are we telling this? We're creating a value called df for data frame, but this is random, a random name. And the idea is to tell Spark, the basic library of Spark, to read in format CSV, because it's a CSV, comma separated value, with infer schema option, meaning that you're telling Spark to infer the type of variable that you're reading for each column. If we don't have this, we could introduce that in this read operation, saying that the first column of the CSV is an integer, the second column is a text, the third column is a date. Instead, we can do an infer schema, and if we don't have weird characters, or we don't have lots of quotes, single or double quotes on words that can mess the recognition of a number or of a text, Spark is most likely to infer the schema. If you have the schema by hand, at hand, better introduce it to avoid problems. We're telling also option header true, that we're telling that it has a header, and we're telling from which file we are loading this. See, so let me open again the chat. Okay, so see that now it's thinking a little bit. It starts thinking, it starts saying, okay, I have to read this file. Better to be prepared. Better to be prepared for something big. Better to start telling each worker which piece of this file to read at each time. See that now it's here working and saying, okay, it is taking time. It is doing some stages of processing. Why do we have one true in quotes? And that's a good question. That's a good question. I think it works with quotes and without quotes. The thing, because it's already optimized for this. The thing is that options. Let me find a way to say it clear. The options in some package, unfortunately, the options are text options. So sometimes, for example, in here, this option infer schema understands Boolean true and false. But I think that header option only understands true as a text and false as a text. I think that they fixed it. Maybe this is from this line. I should correct it from the time that it was not. It was something to be fixed. Technically, it should work with quotes and without quotes. But this is the thing, that some options, instead of expecting true false value, expect a text with the value of the option that can be Boolean or can be other thing. You can test it. and see what happens if you quit the quotes. In case that they, I think that they finally fix it, but I didn't fix the slides yet. So I will write, I will keep it in mind to fix it. So we read this file, and now df is a data frame. And it tells it's an SQL data frame. This means that we can go through this data frame as an SQL table. More or less, it's not like generic SQL, but the operations will be very SQL likely. We can also do MapReduce operations. We can do a take, for example, take 5, and it will return me this. I think that I can also do, well, I can start doing things like count. That count is an SQL keyword and operation telling, please tell me how many inputs do we have. In this case, we have 700,000 rows. We can also tell things like show that it will put a limit to print. But if we do show, here it looks ugly, but this is an actually SQL output. If you're familiar with SQL, MySQL, MariaDB, SQL Server, etc., this is SQL. This is an SQL output that you would expect from other programs, from other SQL clients. So we see that we can do SQL operations. We can print the schema. Df, I don't know why it jumped here. Huh? Df print schema, and we get the schema that it inferred, that mostly integers, but I think that on the top there are some strings, and if it's nullable or not. But if you know SQL, this is basically SQL. Also, we can do operations like select, filter, group by, limit, and also we can do it as an SQL function syntax like. We can do spark.sql and write the classical select from where function and act with this data frame this way. And the good thing is that all the processing for this file will be done distributed by the workers. This means that, remember that at the end, we do this because we want this data frame, in this case, processed in parallel across different workers. So in this case, we have these two workers splitting the work of doing this selection, filter, and grouping by, or limit, etc. To operate with SQL, there's only the detail that we have to register it as a table. That in this case, we do like this. With the create global temp view, what we are doing, if you already know SQL, we are creating a view. It's lots of warnings, but at this time, you don't have to worry. What we're doing is saying that, look, create me a view of this data frame so I can do SQL operations over it. This is just for using the SQL syntax. So the same way that I can do a select, for example, this is the show. This is the classic select serial NO select comma RT division region of SQL, and we get a table, an SQL table, SQL result table. We can do it with the SQL syntax. Now that we registered the name of the dang it, from USA show. Now we have the same. It's what we did here and here. It's the same. It just changes the way of doing this syntax writing. It's exactly the same. If you are familiar with SQL and feel comfortable, go with the SQL. If not, go with the other one, with the classical relational. Also, we can do filtering. That filtering is the where clause. Okay, it is giving me problems to copy and paste. I will go with the directly from the PowerPoint. Okay, let's say that I do the select and I want to filter this is to do a where Puma is bigger than 2060. So it will make this selection, but I can also do this as SQL from classic SQL. Let me show you very quick. I have to go to the notepad and edit it really quick. Let me check that I put the space. Okay. So select from where it's exactly the same. Also, we can do group binds. If we had the word count, if we transformed the file into a table, we could do the same word count using a single line of group by kind of word or count the words, print the words and count them. That's it. So let me see that group by division show. This requires time because now it's not just counting the data or showing some data with the group by. I'm telling it to do a Mapreduce operation, saying for each entry, send it to the worker, group by this division, then count every grouped amount, then from the different workers, reduce again, share the information, and aggregate the different groups that they counted. It's a Mapreduce operation again of I spread the data, do some operation, and when reducing, I keep reducing in cascade, let's say, one by one. And we have the results. And doing this is exactly the same. If I copy and paste, it's exactly the same. Then we can store results because everything that I do here, I'm not just printing this. This is actually a result that I can store. For example, if instead of showing, I can do a variable df1, and now I do df1 show. What I did this is instead of just computing and showing, I'm saying, look, what I'm computing, I want to store in variable df. And by this, Spark is doing nothing, just taking note of, okay, this guy wants to group by division, count it, and store in df. And it's not until I tell, okay, now I want to see what df1 has. It's when it starts computing everything. So it's this laziness of computing. You see, right? You see the when you execute things and when you don't execute yet things. It's when you want to show them or to store them that it starts processing. And every group by, every selection here, every selection, every filtering, I can store it as another data frame. I can create new data frames and operate with them for every operation, and then retrieve them when I need. So remember, that's the thing, that Spark keeps all the operations that you want to do, and it's when you want to show them or store them or do some important operation that it says, okay, that's how we'll do this. Then we can also store we can store it. For example, I'm storing here in a Parquet format. Parquet is one of many formats that Spark has. That basically, oh, what happened here? Let me check. Who's a packet? Let me check the error. Already exit. Oh. Maybe I need to put. I already executed this, so I think I need to tell it to rewrite. As I can't remember which was the option, let me check it really quick on the internet. Right. It's just adding an option. Just a second. Mode override. Okay, that was mode override. It's not a member. Oh, it's not a member unit of this. Now, mode override belongs to the write function and not to the parquet function. It's this builder, this construction software method. So see that now I'm writing, in this case, the data frame into a parquet file. And the thing of the parquet file is that I can not only read again, but I can use it as a table without having to read directly. So I could do something like this, that it's part of the characters, but okay. I could do something. I could read it and start using this PQ file TF. Oh, the tabulator works if you want to autocomplete. Limit 5, show. I can read directly from the parquet file and show things. And I also can create a temporal view, meaning that that I can work directly with the file without having to do a full read operation. Well, I do a read operation, but here Spark is working with this format. That this format is already split. That's the thing. If I store this parquet file in a distributed file system, probably instead of a file in one of the workers, we would have different files in different data nodes. Sorry, we would have, instead of one file in a data node, we would have pieces of this file in different data nodes. So now let's do some coffee break, maybe 15 minutes, and then we will continue. Is it okay? Are things okay right now? Everyone could follow and do their stuff with this. Or any question up to this point? Another question is: are you asleep already, or could you be paying attention to all my yak? Okay, well, thanks to you all. So let's do a 15-minute break. Amalia, are you around?
Yes.
Maybe we can do a short break, 15 minutes, and then we come back at 16:40.
Sure. 16:40 then, in kind of 15 minutes from now. So see you around.
Okay, so see you around. I will also take the chance to do a small break.
Thank you, everyone. Thank you, Josep.
Thank you. See you now.
Josep? Okay, there you are.
I'm back. Okay, so let's continue if everyone's here. Okay. Oh, for dinner, dinner break. Right. We are around the world. Different time. Okay. So let's continue. You still see the screen and everything, right? And the terminal and everything. Yes. Okay. It stopped for some reason. It stopped Zoom, indicating me that I was sharing. But okay. Okay. So let's go for Spark ML now. What we've seen is the idea of Spark, the idea of deploying it as containers, as workers, as masters, etc. And we saw the basic operations, or the low-level operations that we can do, and that we can do also high-level operations like Spark-like, SQL-like operations. But we have more high-level functions in order to do analytics, meaning that we can do analytics like selecting, aggregating data, and filtering data. But we can also do things like machine learning. That's what Spark ML is for. That instead of just getting statistics or or aggregations of data to create models and do prediction. So we have the Spark ML that now it's before it was MLlib, but it advanced to Spark ML. In the version 3, I think that everything's Spark ML. The version 3 is the latest version. We're working with the 2.4 that's kind of stable, but for the next course, I will have to update to the stable version of Spark 3. I hope that they have a stable one. So we have Spark ML. And what's Spark ML about? It's a set of functions of machine learning. So algorithms of machine learning for regression, classification, for clustering, for data, other kind of data transformations, with their fitting functions, evaluation functions, and prediction functions. And they are programmed in a way that these functions are well distributed, meaning that it's not like spreading data and applying a function to every element of data, but if you have to create a model, you have to go usually through all the data or through segments of data and comparing them and moving points, etc. So these libraries are prepared for distribution. For example, using Mapreduce strategy, like I get my data set that I want for training, I spread it or I shatter it for the different workers, and then I train a model for every worker, and then I fuse the different models. So one way of distributing machine learning is to create submodels or local models for every local data set in each worker, and then to aggregate these models into one unique model. If we have, for example, a linear regression, we can have one linear regression for each worker, and then find the average function in this linear regression by averaging coefficients, for example. Or if we have trees or random forests, another machine learning technique, every worker can create its forest, and then we create a forest of the forests. Or if we have some technique like knife bayes, that it's basically counting occurrences on the data set, we can directly aggregate the occurrences and to get the probabilities. So this allows us to distribute the machine learning process and have it done in parallel. So let's do some examples here. First of all, with Spark, we have types of data. We have vectors and we have matrices. And these vectors and matrices can be dense or sparse. Think that with Spark, we are dealing with big data. And usually one of the problems that we find in big data is that we have lots of data, but most of data are zeros. That we have very big matrices that 90% or 80% of the positions are zeros. And we have to load in memory lots of zeros for no reason. So one of the way of representing data, in order to be able to load all this data, even in workers, for each worker, for all the system, etc., is to have sparse vectors or sparse matrices. Basically, instead of having a value for each position of the vector or the matrix, what we have is an index of used positions and a vector of values for each occupied element. This way, we reduce the space used by these vectors and matrices, that everything that does not appear on the index, that is not indexed and valued, is a zero. So what Spark does, one of the things is to work with this kind of sparse type of data. And also, this just for the syntax, Spark likes to work with this kind of representation, Spark ML, I mean, to instead of having a table of features and then labels for prediction, for classification, etc., it likes to have a vector of features and then a label. That's a label point that it's called. We can find that one way, but we also can transform. If we read CSVs, comma separated values, if we read them in this shape, we can transform to this other shape to be processed by Spark ML. For example, let's start. Let's say that first of all, we load the type vector, no? And then I have it here. I've been writing it down from the slides to go quicker. So let's create some data. Here, see that I'm creating data from scratch. A sequence of 3 vectors that are dense, and sparse. Basically, this is if we get this data and we make a show. No. Why you can't show? Because I have to move it to df. If I this like here, if now I say, look, this sequence of vectors, transform them to a df. So now I have a df, and I want to show it. Now I have what I created here. See the different vectors and its label point. It automatically detects that this is column 1, this is column 2, this other is column 1, column 2, and this vector is column 1, and this is column 2. Here it appears represented as sparse, this third row. But technically, it works the same. So it works the same in dense or sparse. It's exactly the same. It's just how it is represented inside the memory of Spark. So it does the same, actually. Let's do some linear regression. Let's say that I want to fit this and do a linear regression. This is that if these features are pointing in space, and yeah, it's a linear regression as is. Oh no, wait, I'm doing a linear regression with more data, not just this. Sorry, this just was an example to show you the representations. Let's say that I'm loading here. Well, first I load the object or the library or the element linear regression, and oh, it's a warning. Okay, I'm loading I'm saying, oh, get this file as data file. This is the name of the file, and read with the format libsvm. This format libsvm is this format here. It means that this data.txt is already formatted in a way that instead of a CSV, that would be like the other table that like here, it loads it in already this format. So we load this data set. It gives me a warning telling me, let's see, number of features option not specified. Oh, it's telling me that it has features prepared as vectors, but it does not have explicit how many features are inside. In case that this file was wrongly formatted, it would crash when I try to train something. Instead, when trying to read it. If in the read I told the number of features 3, 4, or 5, when reading, it would have said, hey, this line has not the number of features you told me, it's bad formatted, error, something like that. Okay, so, but now we have the data set. We can show it. We see the label, and we see that we have, for the features, it seems to have 10 elements, okay? Let's try to do some training, meaning that from these features here, we will try to get to predict the label. For this, we are doing the classical thing that we do in machine learning, that is, first of all, splitting the data, meaning that instead of creating a model from a big piece of data, we split it into parts. We use one part for training, and the second part that we never used for training, we use it for evaluation to know if the model is correct or not. Because if we train a model with the same, if we test a model with the same data we use it for training, it will be almost perfect most of the time, because we're evaluating with just what it saw. We need some extra data never seen for the model to see if the model actually is worth something and it's able to predict new data. So we do from the data set some random split, and I give an array, meaning that please split into parts of 60% and 40%. I give a random seed for this split to be random. And now I have two splits. if I say splits, it tells me, well, you have an array of 2 elements, because I splitted it into data sets. I will recover this. So I will say, look, training is the splits number 0, and I put catch just for you see that we can put things in catch that once computed, it does not need to be computed again if I ask the same operation again and again. So if Spark is intelligent enough, it will catch it by default, seeing that if we're using the same thing several times without modifying it, the tree of operations of Spark, the optimization, would be able to detect it. If not, we can specify it. We can specify it explicitly. Please put this in catch. So I save it in training. I save it in test. I should be able to do something like this, and do something like this, where I have different data sets. Okay, good. And now let's try to fit a regression. So for this, I'm training here the regression that basically, see that I'm telling create a linear regression and set the maximum iterations before converging, in case that this data set will converge. But imagine that you have a data set that you want to limit the convergence of fitting the linear regression. So put here the different hyperparameters of the linear regression. Linear regression does not have many hyperparameters, but I wanted you to show that you can tweak it. And now it is created the model. Now we need to fit it. So we create the model. The model, I mean the algorithm. We created and configured the algorithm, and now we have to fit it. So we will have a model that will be this linear regression that we prepared, and we will fit it with the training data. And that's it. Here it complains with a warning because it is not detecting BLAS. BLAS is the algebraic library that usually systems come with. You can configure Spark to find BLAS. In this case, as I didn't configure anything, it didn't detect it. But basically, it's telling me, hey, if you had BLAS configured, this would be faster, because BLAS gives you operations like fast matrix multiplication or efficient matrix multiplication, etc. You don't have to be alarmed by this warning here at this time. If you want true efficiency, you should install elements like BLAS to accelerate this kind of fitting. So now we have a model. We have a linear regression model, and what we can do is to evaluate. Now we can observe the model. Let's see if I will copy it from here. We can print the model and see the coefficients, right? And see that we have an array of coefficients for the model. I can also do this and see that we have a vector of the different coefficients of this linear regression. And I can also see the intercept, saying that from this model, intercept. You are all familiar with the concept of linear regression, right? You know what the machine learning model is. Basic machine learning is, right? That you train it with data, and then you can use new data for prediction or classification. Okay, then this is nothing weird for anyone. Okay, so we can create this regression, and we can see the coefficients, the intercept, and we can also do now the testing. And for this, if for training we had the fit, for testing we had the transformation. We have transform, saying, look, in predictions, I want to store this model transform test. Basically, Spark is all about fit, transform, and evaluate. If you have some kind of model and you need to predict or transform data, predict data, you are transforming it, meaning that you are passing it through the model to get the result. And this transformation is actually the prediction in this case. So fit, transform, and evaluate. That's the thing. And it's everywhere in Spark ML. Now I can get the predictions and show them. And what I'll see is the feature, the label, the feature, and the prediction for each element. And I can see, so if I can do something like select and do label and prediction, and I can get the label and prediction. This select is what we saw with data frames, because what I'm being returned here is a data frame. You can do SQL operations or relational algebra operations over this. So I can do select, also filtering, etc. And now what I want to do is evaluate, because at simple sight, I think that it didn't match really well. So it seems that for this kind of data, linear regression does not well. But we can get a fine evaluation. First of all, I can load the elements. Linear regression model, I think I already loaded, but regression evaluator. I will save this select here. So I will, to the prediction, select, prediction, and label, I will save it as PAL. So I have it stored, the predictions and labels. I will create an evaluator, an object evaluation, that in this case will be the MSE, the mean square error, meaning that I will do the square difference, the average of the square difference of every element. And then what I'm doing is val linear model evaluation, and I will evaluate this PAL. I separated these two columns on purpose because I want to evaluate one against the other. And it tells me, well, it's a mean square error of 121. Well, seeing I think that we could do better in this case. We can save the model also. We will go through the same data later, I think, with other predictor, and then we will be able to compare. One of the things that we can do is also save the model. Remember that before we saved a data frame by writing, overwriting, and putting into a file. The model is an object. We can write it and overwrite in case that it exists and save as with this name that I gave it. And later we can load it again. If I close the session and open the session again, as far as I can read this file, I can do a linear regression model load and load this file with the model. And here the same model is the exact model that I saved before. So I can do again here transform and do the transformation of the test again, or save it, val results again, and again results again, show. I can save the model and use as many times as I want now that I have saved. More things that we can do the same, but for classification, and it's exactly the same story, meaning that we just load the super vector machines for classification. The super vector machines are usually for regression, but we can use it as a threshold for cutting it for classification. So I will load the same data. I will do it again. Load the same data. I think that. Let me check if it was the same or not, but we could try with the same data. Oh no, it was for the first. It was linear regression data, and now it's libSVM data. Okay. Well, it's data in the point format, and we're loading it. And let's create a model. And you will see that the procedure is exactly the same, meaning that we are doing a split here. We are doing a split of the data set. We are putting aside the training, putting aside the test. We can create again, in this case, a an algorithm. We are creating the linear supervector classification with 10 of maximum iterations, regparam 0.1, all the hyperparameters, you can put them here. And now we have to train it, to fit it, LSBC, yeah, fit. And I give it the training. And now it is training the model. And what I can do later is to do the prediction again here, just like the regression. And I can show it here. See that at the end, the procedure is fitting and transforming. You have data frames. You can select, slice, get, prepare, or join or prepare the data sets you need for training, and then train a model, get another data frame different from training for classification, for prediction, classification, or regression. If you get new data, you can create a new data frame with this new data to get this new data without the labels, because you want to predict something or to classify something and get the classification. So, well, we can also evaluate things. Here, previously, what I did is to evaluate using, let me see, using the regression evaluation. That it has MSE, MAPE, M-A-P-E. You have also the MAE, etc. Now it's classification. So for this, what we need is something that allows us to do evaluation of classes, like confusion matrices or similar, right? For this, we use the evaluator, the multi-class. Here it's the multi-class classification evaluator. And also I'm loading the linear SVCM model because we are going to save it later. So this will be for saving the models. And let's create an evaluator for a multi-class classification evaluator. That will be accuracy in this case. So what we will count is the number of hits that we did, the times that we got it right against the times that we got it wrong. Let's separate again the prediction and the label. So I do this select on the predictions to see labels and the real labels against the real prediction, or real labels against the prediction, not the real prediction, the prediction. And let's evaluate it. Let's do a val SVC in this case, evaluator, evaluate this. And it, well, in this case, it was easy, as you can more or less see here, a prediction of 1. This means 100%. This means that or this data was really easy, or this model overfitted too much. I guess that it was really low data just for testing, but it didn't suppose any challenge to the model, so it made it perfect for the testing data. Okay. If it was real data, I would be really suspicious. Usually, you don't get 100% accuracy in real data. It means that something wrong you did with your model. But it's okay. This is just an example. Most things that we can do, we can save the model again and load it again. It's the same procedure as before. Model write, overwrite, and save the model, and then we can load the model again to use again and again, right? Everything okay since here? Until here? No, until since? To now? Still okay? Okay, so next things we can do, clustering. We can do clustering. I will try to go a little bit quick because I want to show you the streams and then go direct to Mare Nostrum, and we have an hour left. So I will be really quick for this. Look, well, for clustering is exactly the same procedure. I'm running it in a shot, but basically we load the k-means, we load the data with its format, we create the object k-means. In this case, we put two centroids for k-means, and we feed the data set. We tell it to feed it, and we can print the centers, say, from this model, get me the cluster centers, will be this, and for each printed. And it shows me the centroids of these k-means created. And then I can transform data and show the prediction and tell it, okay, from each one, tell me in which cluster it fell. And basically the prediction of a k-means is it fell into cluster 0, cluster 1. I could change this and put more clusters and see if it changed anything. I can evaluate it with a clustering evaluator that looks for the silhouette to see the Euclidean distance between the elements of the same cluster, in this case, and see if it's really compact or it's really dispersed, and see if the clustering is more or less correct. Remember that clustering we cannot evaluate with ground truth because it's unsupervised learning. It's for discovering information. But we have mechanisms to know if the clustering it's plausible or not, if we can trust it, or maybe we should redo it again with other data or other parameters. We can also compute other means of checking the clustering, like the space within clusters, to see if the clusters are really separated or not. And we can save the model and load the model for more data to come, to open new sessions, to share the model with other users or other tasks, and use it after training. And then really quick transformation of vectors. Remember that I told you at the beginning that this is the kind of structure that the Spark ML uses. Well, we have ways here, for example, that I create this as a data frame, for example. Data frame, no? Data set. Show, because it's a data frame. I created this kind of data frame, and I say, well, I would like to have it assembled. So at the end, I want to assemble it and say, look, our mobile user features will be, the features will be these features, and in this case, click will be the label. So I can create a vector assembler, transform the data. Remember that every time that we have some data, we want to convert it in other data, the function is transformed for prediction, transforming for assembling, or whatever else. It's transformed. So at the end, we have output that if I show it to you, you will see that it's the same data, but with features. It created me these features added to every real feature. And if I select it with a I just select the features, or I can also tell select me, click, and I have it in the format of Spark ML. Can I do the other way around? Because maybe you want to transform some data and you want to turn it into a data frame to store as CSV. Well, we can. It's a little bit more tricky, at least in the version 2.4. I don't know if they did it in the version 3 of Spark, but here we have to go a little bit Mapreduce for this, because they didn't create the high-level function for doing the opposite transformation. So instead of having a transform, we have something a little bit more complex. From these features here that we have here, we need to create a new UDF and tell it, look, for each input vector, transform it into array. For each column, transform it, the vector, transform into these features into separate features, create this header here, and now map for each element in my separated features, put them by index, into the corresponding header. This is kind of looks like gibberish. It's kind of complex. If you analyze step by step, it makes sense. But the good thing is at the end, we do select using this expression. It's like we were doing an SQL expression to transform data in a table. It's the same idea. We transform into features. I put it here not for you to start now trying to understand every element, but for you to have it available in case that you want to do some transformations, to have something to start with, and then you complete this with the API and the manual of Spark, etc. But see, for you to see that it is possible to go to one way or another way. And let's go to streams. Well, first of all, everything okay with machine learning? Because we are now going to streams and try to having the streams. I'll also try to be quick because I want for you to have some time for the Mare Nostrum thing, to have at least half an hour of this. So for the streams, what's the idea of the streams? It's another thing to parallelism and serialization, meaning that sometimes we can have some data, we have some transformation for this data, and we do it at once, in parallel, but at once. But sometimes it happens that we have a pipeline, or we have data coming at different pace, at different time steps, and we need to process it. Or maybe we have some transformation to do, and we want to give this transformation to any other application. So we create a chain of events, a pipeline of transformations, and that's what Spark Stream is about. That we have some data that can arrive at different times. We have different Spark applications that they are connected to each other, and everyone runs their application when data arrives, and then when this data is processed, it's sent to the next application. And the next application, when receives the new processed data, processes it again and sends to the next one, until at the end it stores in a database, in a file, it is displayed in some kind of panel, etc. And we can control when to trigger this, when to send it to the next stage, etc. So we will play with two terminals here. Let me see if I can do a split terminal. If I can separate it from this. Let me open another one again. We will have, the idea is that we have two of them in the same machine. Let me check if I can do something like this. I'm connecting to the same machine, and I will do it larger for you to see. Okay. So I'm in the same machine. How the streams will connect? You can do it to open just another terminal in the same machine. We will connect them through TPC sockets. So this means that as far as they can reach through TCP, they will be able to find it, what's happening here with what's happening here. So first of all, let's set up something like this. What I'm doing here, I'm doing a word count, the same thing that we did at the beginning, but now we are doing it in a simpler way, meaning that I'm loading things for SQL and Spark implicit, that's okay. I'm reading a stream. This means that at this point, when I'm reading this stream, and this is just one line, be sure to copy it in one line, because what I'm saying to Spark is to, instead of read the file, I'm reading a stream that in the format of a socket. This is TPC connection, TCP, TCP. It will connect, or it will listen to the current localhost, and it will listen to the 9999 port, and they will load it. So instead of reading from a file, I'm telling that these lines will read from an open socket that will be listening to things that arrive to the machine, or to the socket in this case. Spark is still doing nothing because I didn't tell it to do anything yet. Remember that Spark says, okay, you want a stream reader here, okay? Next thing is I'm telling from each line that you receive, convert as a string because it arrives as bytes from the socket. We need to give it a format. And flat map, splitting it by space. This means that every line will be split by word by word. This is what we did before, a flat map. And then when we have the words of the line, we will do a group by value and get the count. So at the end, this is a word count. This group them by word and give me the count for each word. And here I will have the word count. See that in a couple of lines we did what we did, that horrible thing that we did at the beginning. And now that we have this prepared, well, we will tell it where to output this. This also is one line. From this word count, you will write the stream. You will put the output of this processing. So everything that arrives through this socket will be processed by these lines, and then it will be output as complete. This means that now I will explain you what this means of complete, but in the format of console. This means that it will output through the console. What do I need to do now? Or what we will do now? We will go to the second terminal. We will use netcat. This is used for many things, but we were using it to dump things to the socket 9999, to the port 9999. Now we can write things, but before writing things, we will tell the query that remember that the query is the last thing of the chain, that we have lines into words, words into word counts into query. We will go to our query and tell it to start. Once we hit enter here, remember, we hit enter here and see that value count is empty because I didn't put anything. But if I enter something, suddenly the word count will start working because the query received new data. I can keep adding things, and Spark, or this query that's running, it's listening to the port, is receiving things and is doing a word count of them. See, if I do hola, 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 bbb, bye, again, it receives things and added to the word count. And see that it is adding it. Then what was the complete thing? The complete thing is because I wanted to show all the things new and old. I want to show the count complete, everything that happened. Later we can tell it just to do the updates, the new things that arrive. So I can here just keep adding things, and my Spark thread will be just counting. Do I need to load something for the query to work? To load something? Did you do the netcat and started it? Because if you don't start it, the query start, I think that it will fail, because the query start expects somebody to be already pushing things into the inbox there. Oh, let's redo it again. See, I closed the stream. Let me see if I can do the query start again. So I go to the netcat, intro, then I go to query start, intro, and then I have it started. So first we open the netcat without needing to send anything, and then we do the query start. You only need Spark running here, and the netcat, just a bash terminal here. You must be in the same machine, remember, at this time, or if you're in different machines, you have to have the ports connected. So the netcat, if I was in another machine, for the netcat, instead of okay. So in netcat, see, I closed it. If I was in another machine, let me try something really weird. That netcat host name and port. Well, okay. So for the netcat, I'm telling this machine and the port. Oh, it's not allowing me to bind this. Oh, there's a firewall in the middle. If there was not anything in the middle, I could just connect from another machine to this query here and start sending things. If we lifted this problem, if I exposed this port to other machines, I would be able to connect from other machines. That's it. So from the same machine, obviously I can do it. There's no problem. But from other machines, I just have to assure that the other machine is listening. That's it. So Elias, you could run it. Okay, you could running everything. You can run everything. So and when I close the connection, the query is closed by localhost. That's what we can do. And I put here as output the console, like I did. Remember that I put format console, but I could, instead of console, I could put a socket as a format, put port and host of another machine or another Spark stream. So I could have two Spark streams where one receives the input from the first one, and the other one sends the output to the first one. So, or the first one sends the output to the second one, and the second one has a query listening to the first one. So I could start chaining processes of Spark. Like, for example, I could have a Spark process doing a word count and send the results of the word count, this table here, to another Spark stream process doing some machine learning, doing some fitting some models. Every time that new data arrives, I fit a new model or I update a new model. And then this model, instead of saving into a file in the disk, I can save it as an output for another Spark stream process that reads the model and starts classifying things with data that arrives from another stream. So think that you can make a full pipeline of Spark processes that every time that data arrives, it triggers all the chain of events. So, and also I put here one write stream, but we have more than one write stream, meaning that every time that the query starts, it sends things to the console, but also to another stream, to another file, etc., or to disk, or to some kind of application, a graphic application that's reading a port. Imagine that you have a, I will say a silly thing, but you have a how is called this application from Elastic Kibana. You have a Kibana tweak to receive data from a port. You could send it to its port in the format required and visualize real time this data happening in the system. You could have multiple formats, etc. So that's the thing. Also, that's what I told you. See, I could put this is loading console. This is the, sorry, this is the same, the stream. We could change periodicities. That's what this is about. We're reading it from socket, etc. But in the query, we are triggering it 5 seconds, 5 seconds, meaning that we are triggering the processing every 5 seconds or every time that we have new data, meaning that we have that every 5 seconds, if there's new data, we will wait. We will not trigger at the same moment. We will take a little bit and collect a little bit of data, then trigger it. Or you could do the output mode update. that this means that instead of here the query 2, I will, because it's a value, instead of complete update and query 2 start, I will open the netcat and let's see that I'm adding new things. See that the old things do not appear, but if I tell hola, let's see if it catches the last hola. So it only gives me the updates on the system, not all the data with all the word counts. Only the new things that arrive are indicated. This is the update. See, so this is basically Spark Stream. So you can combine the SQL Spark, the Spark ML, the streams all together to do a pipeline, knowing that all the things that are executed here are executed on the workers. So the more workers you have, the more the master can spread the jobs or admit more clients into the cluster to share the workers with the different clients. So this is the idea of Spark. I put here, you can exit the additional consoles. This second console was just for Spark, Spark Stream. You can shut down everything, I think, because we are going to the Mare Nostrum demo, but we stay around, meaning that we stay with a terminal, but we will connect to the Mare Nostrum. Oh, I didn't do what here says. I didn't kill the Spark. So we can kill the master and we can kill the workers. To have it, to clean the system, to not have this processor running inside your machine uselessly. If I go to grep Spark, yes, out, there's no Spark. I closed the cluster, so you can close it again. If you didn't, you can close if you didn't. You can shut down your computer. Well, don't shut down because we are connecting to Mare Nostrum. I mean, you can shut down if you're using a specific machine. One last thing. We did things in Scala, but the same things can be done in Python and R. Also, you can open a Scala, Python, or R session, regular R, and you can load Spark as the Spark context as a library and open a session with Spark. So imagine that you have your cluster already started, then you open Python, a Python session, then you load, you make a import Spark as always, and you do Spark dot connection or a Spark session dot session, indicating the host and the port, like what we did with the client when we started the client, right? Saying to the Spark shell where's the master and the port. You can open in your Python session a Spark context indicating these parameters, and Python or R will connect to the master, and everything that you submit will be sent to the master. So you can have local applications of Spark, local applications of Python that connect to Spark at any moment to compute anything you need. You can also connect a notebook. A notebook at the end is an interface with a Python or R session behind. So you can open a notebook that connects to a Spark master, and then everything you submit to the notebook can be sent to the Spark master and be computed there. So see that if we use it here, the client, console client, but we can have other kinds of clients, notebooks, Python or R sessions or Scala sessions, etc. Right? And finally, if you want to do some practice or some testing, you can use the standalone version. That instead of creating a master and the workers, you just tell Spark shell master with local asterisk, and it will create you master and the worker processes by itself. And when you shut down this shell, the master and worker will be closed automatically. This is for a local machine to create a quick environment in a local machine for testing things. Usually it's just for testing, for testing your code, etc. Later, if you want to put big data, better use a cluster where the workers are well dimensioned, etc. Right? So let's go to the demo in Mare Nostrum. Every one of you, I guess that you have your credentials because you did stuff with Jordi Torres this morning and you are able to enter into Mare Nostrum, right? Let me open my credentials because I have some credentials. Okay, great. Let me see if I can open it. Okay, so I will do a connection. Oh, I will do it from my regular machine, but please connect to your login node. This is the use your user and password. And the password was okay. Okay, so I'm connected now to Mare Nostrum, to my account. I will go to this directory, CPFS, projects. You will have a similar directory of CPFS projects, but because you know that Mare Nostrum, or if you're about NCT, sorry. I'm on the group 00. I think that you're on the group 01. And this is basically the space of your user. Oh, now. So you will have a directory like this. Why projects? Because when you start from home. And home is a home is a set of machines that keep the disks of your home. And we don't want to use these machines for processing things or to store temporary things, because Mare Nostrum is a very big machine with lots of machines, and every machine has a purpose. We have machines for storing the home and processing things on home, but processing means storing them. We have machines and disks for storing things for projects, for things that we want to get in order to compute in a process. We also have the scratch that we will see in a moment. We have the scratch is the disks that are used for processing things live. So when we launch a Mare Nostrum process, we are fetching data. We want to fetch data from home or from projects, put it into Scratch, and do things in Scratch, in the disks of Scratch. And then when we finish, we store them into the projects or home. But we don't want to start writing things or tweaking data in the homes of our project. Home and better project is just for preparing the data. So here, see that I have this directory, Spark test. And what Spark test has the data that of the packet, the data that you have. It's the image of singularity, different, these examples, let me do it like this. These examples are the word count in R, Python, and Scala. There's Moby Dick, that we will count the words on Moby Dick. And this is the script that we will run in Mare Nostrum that will automate everything. So this is basically, this is the Spark structure that we already know. But Mare Nostrum, we will not run things directly. We do not try to run things in login, because login is a node for entering and submitting jobs. It's not for starting sessions or putting binaries to run. It's just for us to submit jobs to the big machine. It's just for that, this node. So what, meanwhile, let's see if you can access this directory here. Let's see if you can read it in some way. Let's see if you can read my directory. Paste. Because I want you to copy this. Okay, so create this Spark test with recursively, copy it into your directory nct 0001 0 whatever. Do a copy recursive of this into your home directory. Something like into your projects directory. Enter into your projects directory. So be sure that to be in GPFS projects NTC01 / NCT 01 and the number that you are given. Okay. Everyone found their directory, right? You are in your projects directory. So try to copy this Spark test there. Okay. I guess that nobody had any problem, that you all have. I will not copy it, obviously, because it's silly, but because I already have it, but you should have in your projects directory the Spark test folder with the data that we need. Basically, we need the image, the scripts, the Moby Dick, and start Mare Nostrum, and the script of Mare Nostrum. Then let's see what's in this start Mare Nostrum. We have what we will do is to submit this script, and this script what we'll do is to deploy Spark in Mare Nostrum. Mare Nostrum, first of all, will give us 3 machines, because at the beginning of the script it says nodes 3. It will give us 3 machines, 3 random machines from the Mare Nostrum cluster, in exclusive, with this name that you can change the name. You can edit. Actually, the idea is that you edit this. You can use Nano or BI, and you edit this, and you put your name here. But one, I put JLB, my initials, and this is the maximum time of running. This is to avoid that if there's something wrong, for the process not to be stalled for more than 2 minutes. The process will be really quick. So you can put here your name. It will load Singularity and other required things from Intel. And next thing that this will do, again, we are telling it which image we want. And next thing, I want you to edit these 2 lines, because home dir and work dir will be yours. So at this time, for example, I'm at NTC 0, and my user is 0001 0001. Why are we doing this? Because we have our image and the data to process in projects, but I want that the 3 nodes that we receive, or that each one receives, to read things from scratch instead of projects, because projects is not to be scratch. We want to move it to scratch. So everyone has a scratch environment that will be the working directory. We will create if this Spark test inside our working directory, and the first thing that we will do, our script is to copy all our data into the work directory. See, it will copy the Moby Dick, it will copy examples, it will check if the image is already there, and if not, it will copy. I put this just because the image is too big, and if we run this several times, then you can submit this experiment several times to copy only the image once. The scratch thing will remain temporary. So between experiments, you will have the scratch there. And if not, it will copy it again. And we copy also the experiment. So after having the Moby Dick and the experiments, here we will select the experiment, in this case Scala, but you could comment Scala and put the one in Python or in R, right? Then here we configure the workers. we will give the default. That's all the resources. We will not limit them. And we will workers node, one worker per node. We have 3 workers. We have 3 works. We have 3 nodes from Mare Nostrum, and we are telling it that for each node to create 1 worker. We could put, if you change this, we will put more workers inside each node of Mare Nostrum. So if we put 2 from the 3 nodes in Mare Nostrum, we will have 6 workers in total. Next things that does the script, discover which machines we have. So the next thing is to say, okay, you gave me 3 random machines. I need to know which random machines are. Give me, please, their host name or IP. In this case, the host names. So I know where am I, where will be my master and workers. We have the temporary directories, the outputs as we had in our session. And let's start creating the master. What we will do here is in the script, this script will be executed in one or in the first of the nodes that Mare Nostrum gave us. So we can run directly in this, the master, and see that here. See that this is just for singularity, run the master with the host name, with the outputs, just exact we did in our machine. And we put sleep 5 seconds just to give it time for starting. That we know that it's almost immediate, but we put a sleeping time because when we start the workers, they will have to connect to the master. And the master should be already starting. Next thing, we start the workers. We are here. Start the workers. For each node that we have, and for each worker on each node that we want, and this time it will be 1, we will do an SSH to this node, and we will start the modules of Singularity again for each new node, and we'll start Apache Spark as a worker, and this will connect to the host name of the master. So basically, what we're doing is doing an SSH to every available physical node to start a worker. So we are doing this here. So we have our data in storage that will be moved to the scratch, and our script that will start first the master, then the workers, and finally the client. That's this part here, Spark application. We'll start a client, and depending on if we wanted to use Scala, Python, or R, we'll start a shell, a PySpark, or Spark R, and we'll submit. We'll do the client, the shell, the Spark shell or whatever, and we'll submit the experiment. Remember that I told you at the beginning that if we do Spark shell, we get a shell for Spark, but instead of a shell, we can, it's cut here, but we can put as an input, as a pipe, a script. In this case, it will be the experiment.scala, experiment.py, or experiment.r. So we have this script automates the deployment of all the containers and the session and the submission of the session. And when this line finishes, this means that the experiment has finished and the session, the client session has ended. What we will do is to go node by node, killing the workers and the master of Spark. So we will be cleaning our environment. And finally, after the experiments are done, remember that everything that we did was stored or in local or in the scratch. We need to move things from scratch to safety, to project directory or to the home directory. So at the end, we do this wrap up that we create in the home directory a directory with the experiment and the ID of the experiment. Every experiment that you launch has a unique ID. Then we copy everything that we had into the home directory. So we pack things up, and also we copy the results, the result data, and that's it. So yes, I have. Oh, remember that now that you added this, that you added yours, remember to change this. This is important. You have to put your user that it's, first of all, NCT01, because you are in the group 01, and your user. Okay, remember this is important. And if you want, you can put your name here just to see your I think maybe this is too long even. SK and my name. Okay, so everyone has their script ready, because now we are launching it. Oh, this is a summary of the script. So now what we do is to launch the experiment, and we do as batch. We are submitting an experiment, and we submit from this same directory. Start the script, and see, it tells us, look, your batch ID is this one. If I do SQ, what I will see is, I can do it larger now. I can see the queue of the Mare Nostrum for my jobs of my property. Technically, we see our jobs and not spy on the others, but you will see that it has the ID, it has my name, the user, and the nodes that requested, and the nodes assigned. At this time, it is waiting. At this time, it's just waiting to be executed, because I guess that you started it, everyone started things. At some point, it will be prioritized and put it to run into the machines, into the corresponding machines. So at some point, oh, look, our priority means that it's being prioritized. After priority, you will receive this. For example, it gave me the nodes as 06, R2B, 58, 63, and 64. It gave me, and it says it's running. See that it's before it was being prioritized or pending, and now it's running. And if I run it again, it's still running, it's doing its job. So at the beginning, when you copy the image, it takes a little bit of time, but you will see that later it's quicker. So with SQ, just wait. It does not start. It's in known. If it's in known state, means that it's waiting. If it's in queue, it is waiting. Meaning, technically, it will not be cancelled, except you put as cancel. I will not cancel, but you can cancel if you discover that you did a very big mistake and you want it to be removed. You can cancel. At some point, everyone will start. If you do SQ, see, mine is already finished. My queue is empty, so means that mine already finished. Wait a few seconds to do again as SQ to see that it starts. Oh yeah, no, yes, this means that it's 58, 63, and 64. As 63 and 64 are consecutives, instead of a comma, put a dash. If you have four nodes and you have, so it's 58 and 63 to 64. They are consecutives. It's not the dash. That's the just syntactic printing thing. Not a problem. You have 3 nodes. After finishing, if you go to your directory of projects, you will find that your experiment, the directory you created for your experiment, is available because you, at the end, you copied it back. And if you enter to the experiment, you will see that you have the experiment that you submitted, copied back just for recalling what you submitted. Priority. Still waiting. Don't worry yet. Sooner or later you will enter. Think that there's 60 people trying to allocate 3 nodes in an arranged in a 10 machine cluster. I don't know how many machines we have available, but 60 people for 3 nodes for a few machines. So do not worry. There are some jobs that require consecutives. No, I don't think so. See that our script searched for the nodes, asked for which nodes they had. unless there's something related to hardware, meaning that you want nodes from the same rack, from the same block. Technically, the machine in Mare Nostrum, all the nodes are very fastly connected. They have fast connections for not to being an inconvenient. But maybe in some situations you want a specific node or a specific set of nodes. The only thing that comes to my mind is that you want to execute things from the same rack or the same switch. That maybe then you want them to be consecutives. That's my guess. I mean, I never had this need in this environment. So, oh no, this Elias, this very big number does not mean that you are waiting 5 million. I mean, this is see this. Maybe you were put in another set of in another sub queue, and you have another a 5 value instead of a 1 value. So not a problem. See, well, while you finish running things, we see all that in the script. I decided to copy the experiments we run and the output to see if anything bad happened. But it seems that we have from the output from the master and from the 3 workers, output an error, and we have the results here of the word count, and see that we have first the status of our saving success. If we had problems saving, we would have a failure. So the file system already creates a file saying that everything went well or not. And we have part. That means that instead of dumping it into a single file, it saves it as a already partitioned data. And if we do a head of part 0, we see the beginning of the word count. And it's part 0 and part 1. They are consecutives. So if you put this into the Hadoop file system, distributed file system, probably each part would go to a different machine, but you would see it as a single file, because Hadoop file system, which would show you results.data and not showing do this. It would show you results data as a single file, and it would be distributed, but for you it would be transparent. But as we copy it into a hard disk, we see the trick, the different parts data. Should I see the other submitted jobs? With SQ, you shouldn't, because you only see your user jobs. See that I don't see yours here. I think that there's an option for see everything. Help, but I don't know if we are all. So let's. No. Oh, it's all for our queue in this case, or for specific accounts. Okay, it's prepared for having a little bit of privacy, that you don't see all the other jobs waiting in the system. In this case, you see yours, and that's it. I would guess that for every petition, the AD increases, but this does not mean that we have only one counter. Maybe my job and your job go to different queues, and every queue starts with a different counter. That's what I mean for every petition. Maybe you, if I send from different petitions, I get something really similar, but for different users. It's like a national ID that not always are consecutives. Every province gives a starting point of ID for not for working in parallel also. See, that's I guess that you finally would be able, everyone, to submit. Nobody is waiting for the queue. You have distributed file in Mare Nostrum. We have GPDF, and we have the Google file system. We have a distributed file system of Google. I think it was from Google. I think that the G was from Google. We have a distributed file system also. It's not HDFS, but we could set up HDFS with containers or virtual machines if we want persistence, we could build it. And then when we, in the script, when we submit the workers and the master, we start the Hadoop worker, the Hadoop name nodes and data nodes, and we mount our file system if we have it available. At the end, the file system is a bunch of files in some disk. We can move these files and mount this file system as a distributed file system. So in the script, we could copy the different parts of the Hadoop file system to the worker nodes, start the data nodes, and then start the name node telling, look, these are the data nodes. Okay, people still waiting. Don't worry, sooner or later it has to enter. If you messed anything of the script, you should have received an error, or the job run with an error. I guess that you didn't modify. Yeah, your people could run it, right? Some people told me that could run it. Oh, Amalia, Amalia, this is the last part. This is the last part. Just waiting for people to end the job. Anyway,
no pressure.
Anyway, I think that this will be open. The sysadmin will leave it for a few days, because also the things that you do with Jordi, this morning with Jordi, he gave you some things to try, right? That you will be able to access during a few days and trade, because you can enter later and try when nobody is around, in case that something happened. And let's see, because from I guess that you didn't touch anything, right? From the script, aside of the job name and your working directory, that should be yours. You had a priority code. Because we could ask the sysadmin to see if something happened to the queues. So did anybody could finish the job to see that there's not a problem of users? Let me, because it let me do this. So what do you mean this experience? You mean the, what do you mean? Oh, without the reservation, that's technically let me check something. Let me check the mail of the admin, just in case we had anything to do. Maybe they disabled it and they didn't, they forgot to enable again for this session. The reservation name, okay. Yeah, the reservation name SMMR is this. Oh, it should be until, oh, it was open until now. That's o'clock. So maybe something was messed up with the time. There were 16 nodes, but it's curious because I also had this same kind of account. Oh no, it already expired a minute ago. So what I can do is I tell the sysadmin to give a few hours more, and you try to submit it again. Yeah, it just expired at a minute ago. Oh, yeah. Let me ask if it is possible to change this. Okay. Well, I'm sorry that that it was the same. Oh, yeah. The reservation is invalid. It's because it expired just at 6 o'clock. Let me ask again to the sysadmin if he could open a window of to run this, maybe during the ACM summer school, and then you can try to access later and see if it works well and see if it's okay. Well, I'm sorry that you couldn't execute at the end this. You had everything ready. You only had the job to enter. That was the only thing needed, and you would have seen the job running with everything. So that was the last part. That was just the only thing that missed. So let's see if you can be given a window of testing, and then you try this last part. You enter the same. Now that you have the files copied in your directory, you will be able to submit it, and that's it. So thank you everyone for your attention. I hope that you learned something, that it was useful, or that you found things new, and that I hope that it is useful for you in other things. I don't know if you will do things with Spark or with Mare Nostrum or with whatever. You can keep the image of. I added the source of the image, of the Singularity image, if you want to do anything with it and modify or whatever. Well, thank you to you all, and see you at some point, and good luck for everything. In practically, are you using Scala language? I use Scala for Spark because it was native of it was created native for Spark, or Spark was created native for Scala. I usually use R language.
Okay, this is Fabrizio.
Okay. Oh, Fabrizio.
Oh, hi. Yeah.
Hi.
Yes. Yeah. Great lecture. Thank you very much. I see there are still people asking questions. There was the one on Scala.
We use Python. You can use also Python, people. It's technically the same. Just change the language, the functions, and the API is the same. As we're a little bit late, and I think that we have the next session now. I don't want to steal more time from you. You can write me a mail if you have any other question, and we can chat. Okay.
Okay. Very good. Thank you again.
Thank you.
And I think it was another great day. And thanks for the student for their active participation and enthusiasm. So, well, keep going, and to all the students, I'll talk to you tomorrow. Have a good end of the day. Bye-bye.
Bye, everyone. Bye.
Bye, everyone. And thank you very much, Josep.
Thanks.
See you all tomorrow. Bye-bye.